on cryptography. Oh, wrong button. Okay. Yeah, so today we are going to be looking at cryptography, and no, we're not covering cryptocurrency. So yeah. So wait, 1 second, we have technical issues. All right, we are back. Okay, so all right. So today we'll be having a workshop on cryptography. So just as a quick intro, these are your trainers. So I'm Ori, the CTF from Blahaj, and this is Azazel. Yeah. So I think some of you may be coming here with a question on what exactly is crypto and what does it mean to do cryptography in a CTF setting. So to answer this question, we have to go back to the old days. So in the past, people really wanted to keep things secret from each other. So because of that, someone came with a brilliant idea of modifying messages so that only those who know how to reverse modification can reverse it. So this was in the Caesar cipher, which was used by the Romans to transport messages to their generals, as well as the Enigma cipher, which was used by the Germans in World War II. So today, computers now exist with automated processing power, such that ciphers such as your Virginia cipher and your Caesar cipher are kind of like can be brute force now. And at the same time, people of science are a lot more refined. So there's no longer a desire to be for security by obscurity, and they want, in a sense, they want proof that an encryption algorithm is secure, whereby, in the sense that in the sense they want algorithms whereby you know everything there is about the system, you know how the message is modified, but without a key, you actually cannot break the system. And because of that, mathematics and logic are more or less the only ways to guarantee that security that people rely on. So, in cybersecurity, we basically have compartmentalized cryptography to answer 3 different problems. There's a problem of confidentiality, which is how can I ensure only myself and the reader can view the contents of my message? And this is actually a very major problem, as a lot of communication channels are not secure and they can easily be tapped in. Like for example, if you have Wireshark, you can actually use that to listen in on any traffic communication that's coming in and out of your computer. Then the second problem is integrity, or rather, how can I ensure that my encrypted message is not being altered maliciously in transit? Because a message that is encrypted with your own key, someone can just take it, change something, and when the person receives it and decrypts it, they may get something else instead. And lastly, there is the question of authenticity, which is how can I ensure the person reading the decrypted message is also who I intend to send to? How do I make sure that my message arrives at the right destination and is being read by the right person? And so, to answer these 3 questions, we have what we call algorithms or primitives, which are ways in which we use to answer the problems. So for confidentiality, you have systems like AES and RSA. We'll go through those later on. For integrity, we have concepts like hashing. And for authenticity, we have things like digital signatures and MACs, for example. And what we want is we want systems that are computationally resistant, which means we want algorithms that cannot be easily brute force or beaten through other methods using a computer. And we want things that are secure, whereby it takes more time to boot, which requires more time to crack. And if it takes like decades or centuries to crack a system, then we more or less have something that's secure. And in order to achieve that level of security, we base it on what we call very hard problems. We'll go through what hard problems is later on. In the CTF context, which is what Blahaj is about, cryptography is essentially studying and reverse engineering modern cryptographic algorithms. In a sense, we are trying to find weaknesses or vulnerabilities that exist in their implementations and to exploit them. So it can get pretty mathy at times, so we require a lot of math, but the truth is that's okay. And so for some basic prereqs, hopefully everyone is familiar with programming, just basic Python will be sufficient. And we are also hoping that everyone is willing to learn cryptography and everyone is willing to Google if they get stuck as well. And so for the contents, we basically have the introduction, which I'll handle, followed by asymmetric, which Hazel will handle, after which we'll take a break for lunch, and then we'll cover symmetric cryptography, followed by a bunch of training challenges for you guys to do. So before I move on to the next topic of introduction, does anyone else have any questions so far? Yes. Good point. I don't know what RC3 is actually. I just know it's for RC4. Yes. Anyone else has any questions? Anyone else has any questions before we move on with the slides? All right, then we shall move on. So now that we've covered the CIA triad, which is confidentiality, integrity, and authenticity, we are going to move on to what we call data representation. So fun fact, this was supposed to be covered in a reverse engineering workshop, whose trainer isn't here, and the trainer will be talking about this tomorrow. But because cryptography is moved first, so I kind of have to cover this. So we start by talking about how computers can store data, and this is very relevant in terms of how you want to store messages. Because if you want to figure out how to encrypt messages, you need to know how they are stored on our computers. So the basic foundation of computer memory relies on what we call a bit, which is stored in a transistor. And a transistor has two states, charged and uncharged. So it can either be a 1 with its power or a 0 without it. And this is what we call a bit. Okay, wait, one moment, we have another technical issue. Okay, never mind, the slides are back on. Alright. So this is the bit, it can be either on or off, much like how the slide or the screen was on and off for just now. Yes. So we can use that to indicate an on or an off state. And therefore, if you want to store something like a number, we would chain a bunch of them together. And so something like this is basically storing a number. So this is storing the number 2 plus 8 plus 16 plus 64 plus 128. And by deciding whether or not something is on or off, we basically use that to store numbers. And to store something like text. So let's say I have a string called ABC123, and I want to store this in the computer memory. What we do is that we take each letter, so let's say we take the first letter A, and we use what we call an ASCII table. So this is a very big table that basically stores almost every character that you can think of, and each character is assigned a number. So the number goes from 0 to 127. So in this case, we find the decimal character for A, and we see that the decimal number is, wait, can someone tell me what number is linked to the character A? Correct, it is 65. So we take the number 65, and we convert 65 to binary. So 65 in binary is basically represented as 01000001. For those who are not familiar with binary is basically storing numbers in powers of 2. So in our case, 65 is 1 plus 64. So we flip 1 for 64 and 1 for 1 for 1. So it's 1, 2, 4, 8, 16, 32, 64, and 128. And so to store A, we require basically 8 bits, so 8 zeros and ones to store a character. And this is what we call a byte. So a byte is essentially containing 8 bits, and each bit is a 0 or 1 over here. And in order to fill in the rest, we take the second letter, B, we go to the table, find that it's 98, and we write its binary here. We repeat for C, 1, 2, and 3, and once we combine everything together, we basically have a binary string that represents our data, which is ABC123. We can also convert this into hexadecimal to represent them in a different way. But for hexadecimal representation, I'll leave that up to day 3's workshop where you guys will be using that more often. But in terms of cryptography, in order to represent or visualize how our messages or data is being stored, we have ORD and CHR. So ORD is a function in Python that can translate individual bytes to ASCII values. And CHR is a function that can translate numbers or ASCII values into individual bytes. At the same time, if you have already installed PyCryptoDome as we did before, you can use from crypto.util.number, import long to bytes and bytes to long. These basically translate entire strings into numbers and convert entire numbers into strings. So you can actually do a quick demo of it in here. So actually, yeah, I'll just do a quick demo. So you just need to open your Python terminal here, and then just do from crypto.util.number import. We can just put import. We can just import a asterisk here. Once you have imported all the functions there is in the crypto.util.number category, you can start to play around with them and see how we can convert bytes to integers and vice versa. So ignore everything else, just type this line first from crypto.util.number import all. Alright, then there are essentially two functions in the library that we can use. So the first is what we call long to bytes. So if we do long to bytes, let's say like 1, 2, 3, we will get a character which is a open curly braces. This is essentially 1, 2, 3 is essentially the ASCII equivalent of that, and we can do bytes underscore to underscore long, and if we enter a byte string, which is say this. So you may notice, for example, in here, there is a B, a quote, a character, and an end quote. So B quote end quote is basically saying that it's a bytes object. So in bytes along this is actually us telling it that it's a byte string, and in here it converts this character in open curly braces to 1, 2, 3. So you can see they are kind of mapping in between each other. And to further demonstrate this, if we use CHR and we insert a string containing the open curly braces, oh my bad. If we use ORD, you will see that it gets the number 123. So this ORD converts the character inside open curly braces into a number or into its ASCII equivalent. At the same time, if we run CHR with 123, you will see that we get back the curly braces. So this is how Python is. This is how we usually use to translate our strings into numbers and the numbers into strings. So if you want to move on, so let's say you want to express a string hi exclamation mark. One way to do it is to reconvert every single byte or every single character in hi exclamation mark into its number form. So we can do like ORD h, and then we do ORD I, and we do ORD exclamation mark. You'll see that it is basically 104, 105, 103, 183. We can store it as a number by doing, in a sense, base 256. So we do 104. It is the third character from the right. So we raise it by 256 to the power of 2. Then we add 105 times 256, and then we add 33. And this gives us some number 6842657. And if you were to do long to bytes of that number itself, you will see that we actually get back our number hi exclamation mark. So ORD and CHR can only be used to toggle one byte to its ASCII representation. That's why we use long to bytes and bytes to long from the crypto.util.number in order to convert strings into numbers directly through this means. So far, does anyone have any questions that they would like to ask before we move on? Yes, you're at the back. So byte is essentially one character, and multiple characters is what we call bytes. So a byte is 8 bits, and we use that. So byte is basically what we use to store one value. So it stores one character. So in here, our hi string, this is a byte, this is a byte, this is a byte. So there are 3 bytes in here to store our hi exclamation mark. A long is basically another way to represent a number. So when I say long, you can think of it as just a number. So here, this is a long and it's also a number. They are the same thing by definition. Any other questions on data representation before we move on? Yes. Why do we turn this up? So the issue is that, okay, so you know how in like decimal numbers, we have like tens, hundreds, tens, and thousands, right? This is the same logic that's going through here. So because every byte goes from 0 to 255, so we are representing our values in base 256. So in a sense, exclamation mark is our rightmost character, so it is 33. I is our second character, so it's like our tens. Therefore, we put 105 here, and we multiply it with 256 because we're looking in base 256. Yeah. And then H is basically, it's kind of like this is our ones, this is our tens, this is our 100, because it's like 1, 2, 3. So we do 30. So we do exclamation mark plus I times 256 plus H times 256 to the power of 2. Yeah. Yes. Yes, 2 multiplication is instead exponentiation, so it is powering. Alright, any other questions regarding this demo? Alright, then we can move on. I'll send a screenshot of this in the training chat once, in the training chat later on. Yep, so if you want to reference the demo, you can go to the training general in Discord and you can see it there. Alright, so with that in mind, we return to our slides where we have essentially covered all this to data representation. So this is how we represent our messages or our strings as numbers. And now I'll pass the rest of the morning to Azazel, who will be covering asymmetric.
Hello everyone. Before I start, can I just get like a quick show of hands? Is anyone here familiar with modular arithmetic? No one? Okay, that's great. That means that these slides will be very useful. So first, let's just explain what are asymmetric schemes, right? So you know in cryptography, obviously you want to encrypt and decrypt messages. And with asymmetric schemes, you actually have 2 different types of keys. A public key that's made public to everyone, and a private key that only the person who made the key knows. And security depends on the confidentiality of the private key. So if you can see here in this little diagram from Wikipedia, let's say we have this asymmetric scheme that is being used to encrypt messages by Alice. Alice will generate 2 keys, a public key and a private key. Alice will distribute the public key to everyone, which then they can use in the encryption routine to generate a message. But this message, once encrypted, can only be decrypted with Alice's private key. So this is why keeping the private keys confidential and private is very important. Which is also why recovering the private key, well, let's say you're an attacker, right? You see this message being sent to Bob to Alice and you want to know what it says. But in order to decrypt it, you have to know Alice's private key. So recovering the private key for an attacker must be at least computationally infeasible or impossible for an attacker to do for the scheme to be considered, well, secure. Okay, so remember how Laurie said there's going to be a lot of math just now? Yeah, there's going to be a lot of math from here on. So we'll be going through these main concepts. I hope all of you are aware what divisibility and primality means. Yeah, so I'll be explaining all of these. Please ask questions. Raise up your hand and ask questions anytime you get lost. If once you get lost, it's going to be really hard to get back on track. Yes. So without further ado, our first glimpse into math, right? So I'm sure all of you know what a prime number is. It's a number that's divisible only by 1 in itself. Examples include 2, 3, 5, 7, 11, and so on. And here's a new concept that you might not have heard before, the greatest common divisor, or the GCD of 2 numbers. So the GCD of 2 numbers, as the name implies, is the largest common divisor. So it's the largest integer that divides both of them. So for example, okay, there's a typo here in the slides already. So GCD 312 is supposed to be 3, not 4. Because, well, 3 is a prime number, so its only factors are 1 and 3, right? And the factors of 12 are 1, 3, 1, 2, yes? Okay, that's another name. Greatest common divisor and highest common factor. But personally, I prefer the term GCD because that's what almost everyone uses. So GCD of 3 and 12 is 3, not 4, because 3 has factors 1 and 3, 12 has factors 1, 2, 3, 4, 6, 12. And if you take the greatest common integer between both of our factors, it's 3. And the GCD of 15 and 36 is also 3. If you write out all the factors and find the highest common one, you also see that. And furthermore, two numbers are said to be relatively prime or co-prime if they have no common factors other than 1, which also means that their GCD is 1. Any questions so far? No? Everyone clear? Okay, good. Let's introduce another new topic called modular arithmetic. So let's introduce a new definition of like equals, right? You see here we have equals with 3 lines. This is called congruent. And so for any 3 integers a, b, and m, a is said to be congruent to b, which is written with this 3-line equal symbol, modulo m, if a minus b is divisible by m. It's a very abstract definition, but basically what it means is that, let's say you do modulo 5, right? And you count 0, 1, 2, 3, 4. Once you reach 5, you kind of loop back to 0, because 5 minus 0 is divisible by 5. So under modulo 5, 0 and 5 are kind of like the same number. So we can write 0 is congruent to 5. And by the same logic, 5 is also congruent to 10 and 15 and so on. And you can also work in the other direction. So minus 5, minus 10, they're all congruent to 0 modulo 5. Of course, now you can consider what 1 is, and 1 will be congruent to 6, and 11, and so on, because of the looping around thing.
So it's like kind of like 5, the term is 5 and plus 10, so the term is congruent to n is 5. In this case, I don't know.
Okay, so yeah, another definition of congruent is that. Yes. Okay, so you said 5n plus 1, right? That's correct. So you can see that the numbers here, right? They're all of the form 5n plus 1, where m is an integer. So essentially, when we're doing modulo 5, you're separating the numbers into groups that based on their remainder when they're divided by 5. So the first line here, they all divide by 5 cleanly. They leave no remainder. Second line, they have remainder 1, remainder 2, remainder 3, remainder 4, and so on. Okay, here's another diagram. This time is modulo 12, right? So you can see it's like a clock. You go from 0 all the way to 11. And then once you reach 12, it has like the same position as where 0 is. So modulo 12, 0 and 12, and 24, and 36, and so on, are all kind of treated as like the same number, right? And the same thing happens for 1 and 13, 25, 37, and so on. Anyone confused? Any questions? Okay, then I will arrow someone randomly to check for understanding. This is good. So let's say we're working under modulo 7, right? Under modulo 7, can anyone tell me what's a number that's congruent to 2 modulo 7? Yes, negative 5. What did you say? 2. Okay, yes, trivially 2. Any other examples? 4? Okay, no. So under modulo 7, right, we know that if number is congruent to 2 modulo 7, then the remainder has to be 2 as well when divided by 7. So the numbers that have a remainder of 2 and divided by 7 are 2 plus 7, which is 9, 2 plus 14, which is 16, and so on. So hopefully that wasn't too hard to understand. Yeah. Let's move on. Now let's do arithmetic, because it's called modular arithmetic. So addition, subtraction, and multiplication work the same as normal, right? Let's say you want to calculate 7 plus 8 modulo 12. You know 7 plus 8 is 15 normally. And then modulo 12, which is basically just taking the remainder when divided by 12, is equal to 3. Because 15 modulo 12, 15 when divided by 12, leaves a remainder of 3. So 7 plus 8 is equal to 3 modulo 12. Similarly, subtraction, 7 minus 8 is equal to minus 1. right? And minus 1 is congruent to 11 modulo 12. Because let's say you start from 0, right? And you go backwards 1 to minus 1. That's kind of like the same as starting from 12 and going backwards 1 to 11 because of how modulo works. If you remember, like there's a cycle here, right? So modulo 12, if I'm at minus 1, it's actually the same as 11. Yes. And multiplication, oh, I have a clicker, I forgot. Okay, so multiplication, 7 times 8 is 56, right? Now modulo 12, that means, again, we just take the remainder when divided by 12, which happens to be 8, because 56 is 48 plus 8. So the 3 addition, subtraction, multiplication basically work the same as usual. And again, I'm going to arrow someone to do math for me. So, would anyone like to tell me what 3 times 4 is modulo 12? You with the BlahajC. Hello. Would you like the answer? 0? Yes, that's correct. Congrats. Because 3 times 4 is 12, which leaves no remainder when divided by 12. So 0. Yay. So we have one last operation remaining, which is division. So it's a bit more complicated. Notice how we have here 7 times 8 is equal to 8 modulo 12, right? Does that mean we can divide by 8 on both sides? And can I say that 7 is equivalent to 1 modulo 12? Obviously not, right? That's just not true. So actually, for division, if you look at the multiples of 8 modulo 12, notice how it goes 0, 8, and 4, because 8 times 2 is 16, and 16, the remainder when divided by 12 is 4. It goes 0, 8, 4, 0, 8, 4, right? So it repeats in the loop with only 0, 4, and 8 in it. And if you look at the multiples of 5, you see 0, 5, 10, 3, 8, 1. So the thing that's different when you're looking at the multiples of 8 versus the multiples of 5 is that the multiples of 5 actually go through all possible numbers between 0 and 11, while the multiples of 8 only go through 0, 4, and 8 before repeating. And why is this so? It's because the GCD of 8 and 12 is 4, right? Okay. Apparently, most people are lost already, which is very sad. So, okay, let's just come back to modular arithmetic first. I'm going to ask more questions. Let's say we're working under modulo 15 now, and I'm trying to calculate 11 plus 12. Let me arrow around the person. Front row, you. Yes. Can you tell me what 7 plus 12 is modulo 15? It is indeed 4. 7 plus 12 is 4 modulo 15 because you just plus and then after you just minus. Okay, so you calculate 7 plus 12, which is 19. And you want to find a remainder, right? So you divide by 15, and that gives you 4. Yes. Okay. So seriously, is anyone like lost already for this slide? No. Okay. So again, I hope you guys all understand this little example I'm using to motivate division under modulo. So for this slide, right, the multiples of 8 modulo 12, if you just calculate it, it is indeed 084, 084, right? Hopefully that's also not too hard to see. And the multiple of 5, well, 5 times 0 is 0, 5 times 1 is 5, 5 times 2 is 10, 5 times 3 is 15. For modulo 5, that's modulo 12, that's 3, right? Because 15 divided by 12 leaves a remainder of 3. And 5 times 4 is 20. That's equivalent to 8. Because 20, when divided by 12, leaves a remainder of 8. Okay, 20 is 1 times 12 plus 8. Yes. And 5 times 5 is 25. And 25 is 2 times 12 plus 1, right? So 25 is congruent to 1 under modulo 12. Anyone have any questions with this slide? Okay, hopefully not. So again, I hope you guys noticed that multiples of 8, they only go 0, 8, 4, and the multiple of 5, they go 0, 5, 10, 3, 8, 1. And they actually contain every single number from 0 to 11 modulo 12. Okay, so yes, this slide. So the greatest common divisor of 8 and 12 is 4, right? Because 8 is 2 times 4, and 12 is 3 times 4. So hopefully it should be intuitive why the multiples of 8 mod 12 are all multiples of 4. Because if you think about it, let's say we're calculating multiples of 8 normally, right? So 8, 0, 8, 16, 24, 32, they're all multiples of 4, right? And because we want to find the modulo 12, which means we're taking away as many 12s as possible, we're subtracting as many 12s as possible. If you have a multiple of 4, and you subtract a multiple of 4, it's still going to be a multiple of 4. So that means that multiples of 8 modulo 12 are all going to be multiples of 4, which is 0, 4, and 8. Now, can we divide a number, say 7 by 8? Well, no, it doesn't make sense, right? Because you can't even get 7 when you multiply something by 8, since you can only get the multiples of 4. So you actually can't divide non-multiples of 4 by 8 under modulo 12. Does this make sense? Okay, hopefully. So we also can't divide 0, 4, and 8 by 8, right? Because we'll get multiple answers. See, if we have 0 and we try to divide it by 8, normally in normal integers, we get 0, right? Because 0 times 8 is 0. But under modulo 12, you see that 8 times 3 is also 0. 8 times 6 will also be 0. And 8 times 9 will also be 0. So when we try to do 0 divided by 8 modulo 12, we'll get multiple answers. So we'll get answers simultaneously, 0, 3, 6, and 9 all at once. Which is not very good. We don't want that to happen. So that's why we can't divide 0, 4, and 8 by 8 either. So if we can't divide by non-multiples, if we can't divide non-multiples of 4, and we also can't divide multiples of 4, we just can't divide by 8 in general, right? So this is a generalization, right? We cannot divide by a number d modulo another number n if their GCD is more than 1. Yes, both numbers must be co-prime for it to be possible to divide. Everyone following so far? Okay, let me ask more questions then. Let's say modulo 24, can I divide by 7? No? Why? Okay, GCD of 24 and 7 is not 3. GCD of 24 and 7 is actually 1 because they share no common factors, right? 7 is a prime number, so unless 24 is divisible by 7, you can't have the GCD be larger than 1. So since the GCD of 24 and 7 is 1, you can actually divide by 7 modulo 24. I don't have an example for this, but hopefully it's okay. Let's say 7 times 8 again, right? 7 times 8 is 56. Modulo 24, that's equal to 8, because 56 is 2 times 24 plus 8. Yes? So that means that was a bad example. Okay, let me think of a better example. Can I divide by 3 under modulo 18? How about you? White shirt with stripes. Divide by 3 under modulo 18. Yes? Okay, that's very concerning. The answer is no, because what's the GCD of 3 and 18? Yes, 18. 3, right? So the GCD is larger than 1, right? So you actually can't divide by 3 modulo 18. Okay, Everyone's confused. That's very sad. So let me just reiterate the last point, right? Under a modulo n, if we're trying to divide by d, we need for d to n to be co-prime, for the GCD to be 1, for division to be possible. So if we're trying to divide by 3 modulo 18, right, we can't do that because the GCD of 3 and 18 is 3. So we just can't divide. It's similar to the situation here with division by 8 modulo 12. Okay. Sorry, let me just ask one last question. Modulo 17, can I divide by 4? How about you in the red shirt, third row? Modulo 17, can you divide by 4? Division by 4 mod 17. Are you asking ChatGPT? Okay, well that's correct because 4 and 17 has GCD of 1, right? They're co-prime. So you can divide by 4 modulo 17. Okay, division is well defined. Okay, hopefully that was enough examples for you guys to get less confused. Now we're gonna again introduce a new concept called the Chinese remainder theorem. You've heard of this? That's great, okay. So let's say we have an unknown number, x, and we happen to know the remainders modulo several modulos, n. So we have this series of congruences that x is equal to a1 mod n1, x is a2 mod n2, blah blah blah. What the Chinese remainder theorem says is that it is possible for us to compute this remainder modulo the product of all of these moduli. Okay, so that might sound a bit abstract, and don't worry, I have an example for this. So if you've done Math Olympiad or like you've been interested in math before, you might have seen this kind of questions where, oh, we have an unknown number of things. If we count them in threes, there's one thing left over. If we count them in five, there's two things left over. If we count them in sevens, there's two things left over. So this is actually the setup for the Chinese remainder theorem, right? Because if we let the number of students be x, what I'm saying, if I'm saying that if we're grouped in threes, one student is left over, is I'm saying that x is equivalent to 1 modulo 3. Because the remainder of x when divided by 3 is 1, right? There's one thing left over. And similarly, we have x is equal to 2 mod 5, x is equal to 2 mod 7. So now we can use the Chinese remainder theorem to calculate their the value of x modulo the product of these modulos, so 3, 5, and 7. So we can calculate the value of x mod 105, which turns out to be 37. Everyone clear? Where did I get 37 from? So you actually have to calculate 37. I'm not including the calculation steps here because that's going to confuse you even more. But generally, if you guys want to know how to calculate, you can come ask me later. We can use this function called CRT from the package simpy.ntheory.modular, which is why I asked you guys to install simpy earlier. So this function here, when you give it the moduli, like 3, 5, and 7 here, right? And you give it the remainders, 1, 2, and 2, it can actually calculate the answer for you. So I give it 3, 5, and 7, and 1, 2, and 2 to mean that I want to find the number x such that it's equal to 1 mod 3, 2 mod 5, and 2 mod 7. And it spits out this tuple of values, 37 and 105. This means that the answer I'm looking for is that x is equal to 37 modulo 105. Everyone following so far? Okay. Let me ask more questions. How about fellow using the MacBook front row? You, yes. Why don't you use the CRT function from simpy to solve? Let's say I have some apples, right? And I group these apples in groups of 5, and I have 1 left over. When I group them by 7, I have 3 left over. Yeah. So when I count in 5s, I have 1 left over. When I count in 7s, I have 3 left over. When I count in 9s, I have 5 left over. just try this example. So I have a number x that's equal to 1 modulo 5, 3 modulo 7, and 5 modulo 9. So x is equal to 1 modulo 5, 3 modulo 7, and 5 modulo 9. So in the first argument of CRT, you put in list of all the moduluses, right? So in this case, it will be 5, 7, and 9. That's the first argument to the CRT function. In the second argument to the CRT function, you put in the list of remainders, which in our case is, well, not this example, the example I just came up with. It's 1, 3, and 5. So if you put that in, 311, 315, which means that the number I'm looking for when it's equal to 311 modulo 313. And you can see that 315, I think it should be equal to 5 times 7 times 9. And if you try to calculate yourself, 311, right? When you divide 311 by 5, you get a remainder of 1. 311 divided by 3 is a remainder of, 311 divided by 7 should give you a remainder of 3. 311 divided by 9 should give you a remainder of 5. Anyone still confused? Yes? Okay, yes, that's a great idea. Okay, so our example just now was, we have the number x, right? And you have x is equivalent to 1 mod 5, x is equivalent to 3 mod 7, and x is equivalent to 5 mod 9, right? So to solve this series of functions, we use the CRT function, right? Oh, okay. So again, you can see here, the first argument is going to be our moduli, right? And the second argument is going to be a list of our remainders. So in our case, our moduli are 5, 7, and 9, yes? And our remainders are 1, 3, 5. So to calculate this, we will do CRT, bracket, 5, 7, 9, 1, 5. Yes? And now if you try writing this, it should give you 311, 313. Similar to this, this means that x is equal to 37 modulo 100. X is equal to 37 modulo 105, right? Alright, let's continue. So for the previous example, the output of bracket 37, 105 meant that x is equivalent to 37 mod 105. Yes. So here, if we get 311, 315, this will mean that our solution of x is equal to 311 mod 315. So what can we do with this information, right? Well, let's just say, since it's a Cochrane relation, so there's infinitely many solutions to this, right? So let's take the smallest one. Let's just do x equals to 311 as a number, no modulo involved. And let's try to check if this satisfies these congruences here. So 311 mod 5, right? Well, we all know 311 divided by 5 is equal to 1 because log digit is 1. Yes, 71. 71 divided by 9 is 308. Yeah. Okay, yes. So 311 modulo 5 is equal to 1. Hopefully, obviously. 311 modulo 7. It should be modulo 3. And 311 modulo 9. Well, you know, to calculate the remainder of a number when divided by 9, just add up all its digits, right? So literal root. So 3 plus 1 is 1, is 5. So we have indeed checked that x equals to 311 is a valid solution to this series of congruences. Okay? Anyone confused? Okay, hopefully, can you guys see what I wrote on this board? Actually, people at the sides in the back room. I'm assuming that's a yes. Slides are absolutely unreadable, but whatever. So let's continue to the next slide. Right. Let's go back to modular arithmetic. So we know that division doesn't work well when your number and your modulo are not co-prime. When they share a factor that's not 1, right? So we'll just work with co-prime numbers from now. So let a and m be co-prime, and we consider the powers of a modulo m. So the powers of a go 1, which is equal to a to the power of 0, a, which is a to the power of 1, a squared, a cubed, and so on. Now, you can imagine drawing this as like a graph, right? Each circle corresponds to one number, and the arrow means multiplied by a. So here's fact number 0. Every single power of a will also be co-prime to m. And okay, let me arrow someone to tell me why. You, green shirt color. Can you tell me why any power of a will also be co-prime to m? Why would any power of a also be co-prime?
It's very low.
So the reason why every single part of A will be co-prime to M is because we let A and M be co-prime, right? So they already shared. Oh right, yes. So sorry. Oh, where's that? Okay, yes. As I was saying, the reason why any power of A will also be co-prime to M is because you're multiplying a number that's co-prime to M to itself, right? Obviously, this wouldn't add any extra factors of M because A is already co-prime to M, right? So they have no factors in common. If you multiply A by itself, it does not add any factors that M has. So this whole series of numbers will have no factor common with M. Is that a clear enough explanation? Yeah, hopefully that's a clear enough explanation. So, fact number 2, right? If we keep drawing out this chain, 1, a squared, and all the way to a to the power of I, right? There must exist a cycle. Why is that? It's because modulo m, we only have n possible values because we're taking the remainder, yes? So the values go 0, 1, 2, 3, 4, all the way up to n minus 1. So there are only n possible values to take, right? Obviously, I can't continue this chain forever because otherwise it would imply that there are an infinite number of values. So once you continue this chain, eventually you must come back to a number that you've already reached before. Is that clear enough? Yeah. So because we only have a finite possible number of values, it must repeat somewhere. Okay, again, please, if you are not clear, please just raise your hand right now. Okay, yes.
Can you explain again?
Okay, so this graph here, right? This represents me starting from 1 and multiplying by a over and over and over and over and over and over again. Yes. let's think about what happens if I do this for a very long time. Eventually, I will come back to a value that I've already reached before. This is because under modulo f, we only have n possible values, which is 0, 1, 2, all the way to n minus 1, right? So I can't have the chain continue on infinitely, yes. So there must be a repeat somewhere. Okay.
Yeah.
Is that clear? Okay. Anyone else confused?
I thought it was.
Okay, yes.
I thought it was
Multiply it, we'll go back to the same value because modulo f, we have n possible numbers. So eventually you have to repeat, right? You can't go on infinitely without ever repeating. Okay. Any other questions? Anyone else confused? No? Okay, good. So this is fact number 1. Next fact. Remember just now here, right? We drew this graph, and I just assumed that there must be a repeat somewhere. So I drew this repeat somewhere within the chain. But now, we'll see that there can't actually be this tail in this graph. Because GCD, we define A and M to be co-prime, right? Which means that we can divide by A. So, because we can divide by A, if we had a tail here, right? Let's imagine we take a to the power of I and we divide by a. If such a tail existed, because both of these represent multiplication by a, right? This would mean that a to the power of I divided by a, which is the backwards arrow, will give us 2 possible answers. Which is not very good, right? Because we already defined a and m to be co-prime. So division cannot have 2 possible answers. Which means that, therefore, this kind of like T intersection, three-way intersection cannot exist. Which also implies that the part where it repeats must be here at the front, right? So if there was at the front, you would just have a complete cycle with no like junction, T junction like just now. So we have that the graph is a circle. It's because it starts at 1, it goes to a squared, all the way, then comes back to a1, and 1, which is where it repeats. Is that clear? Anyone has any questions? All of you look super lost, but I think there's an example in the next slide. So, yeah. So let's look at examples with real numbers, right? Let's say I'm investigating the powers of 3 modulo 7. So I start at 1. 1 times 3 is 3. 3 times 3 is 9. Modulo 7, that's 2. 2 times 3 is 6. 6 times 3 is 18. 18 1 times 7 plus 4, right? So 18 is 4 modulo 7. 3 again. 4 times 3 is 12. 12 modulo 7 is 5. Modulo 7 is 1. So you can see we do indeed have like a circle, right? It starts at 1 and eventually it goes back to 1 and then it repeats. Then we multiply by 3. Yes? Now let's consider the same case, still modulo 7, but now we're doing powers of 2. So we start from 1 again and we multiply by 2. That gives us 2. 2 times 2 is 4. And 4 times 2 is 8, which modulo 7 is 1, right? Because 8 divided by 7 has to reduce to 1. So we've already reached back to 1. Obviously, this must be a cycle again, and it repeats. Okay, anyone lost so far? Everyone clear? Everyone keeping up? Okay. So, now that we've demonstrated that exponentiation must always give us a circle, right? The natural question to ask is, hey, we're doing this both under modulo 7, right? Why is this circle so much bigger than this circle? See, this thing goes through every single possible remainder of modulo 7. Well, this thing only gives us 1, 2, and 4, right? So, why are these two circles, the sizes of these two circles different? And, like, more generally, what possible sizes of circles are there, right? So obviously, the biggest circle possible will contain all numbers x, 1, and m such that they're co-prime, right? Because if you remember, from this slide, any part of A will be co-prime to M, right? Which means that all the numbers in this circle must be co-prime to M. So we have an upper bound. And the smallest circle will only have one number, which is 1, right? 1 raised to any number is equal to 1. So it just goes back to itself. That's a circle with only one thing. Any other size is possible. So here, let's just define this notation. This symbol is called phi. So we let phi of M to be equal to the number of integers between 1 and M co-prime to M. Everyone keeping up so far?
Okay. You lost us. You lost me at 5.
And also at 5. Okay. You can just so phi is just a way to represent the number, to calculate the number of integers between 1 and that's co-prime to M, right? Because we see we have this condition popping up a lot. So we want to quantify the number of numbers that's co-prime to M. So maybe it would help if I give some examples. So let's say we calculate. Would it be troublesome? So we want to think about the number of numbers phi of M. Right? Can everyone see what I'm writing? Hopefully the marker is a bit faint. Yes. Phi of M. So this again counts the number of integers between 1 and M that's co-prime to M. So we can calculate it for some example integers like what's a good number? 12. Okay. So what's phi 12? If you want to calculate this by hand, first you can write out all the numbers from 1 to 12, right? 1, 2, 3, 4, 5, 6. And again, we're looking for numbers that are co-prime to 12. So it goes 1 to 11. And then what are the numbers that are co-prime to 12? We know that 12 is divisible by 2, 3, 4, 6, right? So immediately those numbers are gone. 8 is a multiple of 2, right? So it shares the common factor 2 with 12, so it also has to be gone. 9 also has to be gone, because both 9 and 12 are reduced by 3. 10 is also gone, because there's 2 in there. So we have that phi of 12. So the numbers that are co-prime to 12, numbers that are co-prime to 12 from 1 to 12 is only 1, 5, 7, and 11. So we have that phi of 12 equal to 4. Okay? So let's do another example. What's phi of 7? Okay. So again, we can start by writing out all the numbers from 1 to 7. But if you're smart, you guys notice that 7 is a prime number, right? So no number can share a common factor with it unless it's a multiple of 7. But we're only considering numbers from 1 to n. So all of these numbers are actually co-prime to 7, which means that phi of 7 is equal to 6. Okay, is that clear?
Yeah, and then the phi of prime number is very high because.
Okay, so you don't have to care that much about phi. You don't have to care that much about phi right now. All you need to know for now is that it counts the number of numbers that's co-prime to its ordinals.
Guys, we're having some technical issues with minute. So give us a number of time. Anyone has any questions on asymmetric equality, raise your hand. So you guys should answer your question.
My CPU over until don't know how already.
I got
Bro, I came here for my CES specialty is OSIN. I'm a social hacker. OSIN, which is like the one we go social media stuff people. Google and then you like track down people using like the smallest of links where you could be like their LinkedIn, then basically from like the starters and stuff, you're supposed to learn their full name, username, any accounts, maybe what crypto they have, like where they live, down to the city, like maybe not to like Bangkok City. But yeah, I think that's really only lah. Maybe you can find the IP address.
Okay, hopefully you guys aren't that lost.
Can you send the PPT over because we definitely need to reread this. Otherwise, we're never gonna understand.
Okay. Okay, yeah, the slides will be sent after today ends.
What the hell?
Anyone else has it? What is co-prime? Co-prime is when two numbers have no common factor. So only one.
Because one is a factor of the
Yeah.
Oh yeah, and then correct it. Any number, any prime, phi of a prime number is always the prime number minus one because the numbers between that number and the other numbers is just 1 to 1. How do you say? The phi of 7 is 1, 2, 6. Get it? The possible numbers that could be how do you say co-prime with 7, you just miss out the 1, 2, 3, 4, 5, 6.
Yeah.
And since 7 is prime itself, the rest of the numbers can't be, there's no factor that will like correlate to 7. So therefore, all the numbers can be counted are part of phi. So the rest of phi of the prime number is just prime number minus 1. So 11. So phi of 11 is 10. Phi of 13 is 12. And so on and so forth. It's the easiest bit of phi. The phi of the prime number is just the number of prime number minus 1 because it's just the rest of the numbers operating on 1. Right? Phi of
Okay, 5 minutes break since we're installing drivers for the growing tablet.
We're gonna have we need a Wacom for freaking cybersec. Oh my god, what did I say? No, they have a Wacom. They're gonna like put a Wacom on this thing. Wacom, the one that normally all those like storyline animators use to like draw their animations. I thought I signed up for cybersec. What the hell?
Alright, so I can kind of like gather that some of you may be very like confused with the math and what's going on. It's part and parcel of asymmetric probability. So while we're trying to give you guys an introduction to asym, once we get into the crypto systems or the cryptographic primitives involved, it will get easier from there. It's just that now we are doing the theory heavy portion, which can be very hard to understand, and don't worry about it. Yeah, it will take some time, but the more you're exposed to it, the more it will slowly make sense. Yeah, and this will be basically And later on in the afternoon, we'll be going to symmetric probability, which I will assure you is a lot easier to understand. And yeah.
There's like SHA, MD5, all this. Most of them you just like click and drag and then you just like you can add more and then drag and it'll just come up. But it's fast, right? We drag and drop. For some reason I can get that. I thought, no at all. Not even scratch my cookie. Damn. You are so cool. to the world of brain burning.
I signed myself on them.
Shit, like, I mean, hey, I mean, it's good and bad. If you're smart enough, maybe you can hack, you can use this to hack into, I don't know, insert big company here. Next time you play some random computer game, just start hacking shit, and then you just have control. And the worst thing was, I thought this is a good sector to come into. Turns out my brain's gonna die before that happens. Harry from 5 years ago, you should have not made that decision to start coding. Why? Because this is what I'm doing right now. Not that bad. This. Yeah. At this rate, I guess it'll be more entertaining next. Yeah. I forget which one it is. Elective history. Yeah, I don't like geography. Jokes. I mean, everyone knows about Hitler. He's famous for Hitler. No one knows insert rock here. Right? Like, I mean, even in Sec 1, Sec 2, you have that one good ass classmate who's suddenly as good as the highest Hitler in the middle of slash class.
What exactly was the Oh yeah.
No, it's, oh yeah, Sec 1, Sec 2, you guys know about Singapore, but then Sec 3, Sec 4 is Hitler. Like, we, yeah. Yeah. The only good thing is I know how to memorize. The problem is if you're gonna give me bad theory, I'm gonna fuck it. Yeah, because my brain CPU is more like I'm more of a storage heavy person. No, my RAM is very bad.
I think that's what short term memory was.
Yeah, also short term memory also. Yeah. This I did for O levels for physics and chem. Like the last few days I sacrificed two of my subjects and I started cramming sciences. It worked. I started cramming and it worked. My higher Chinese and my humans. I just pray I don't piss up. That one's okay lah. I can't understand. It's not as deep. No, I'm not doing poly. Poly is EL. And also, higher Chinese, the only language you can use is technically English and higher Chinese. It's just a minor school. Oh yeah, yeah. Thankfully mine is our school is higher Chinese. Yeah, I mean -4 isn't that what unless you go to the glory point. Oh, the JC is what? That 1R5 next to Poly Max 3, and you have to have one less subject. Fuck it. Part of the transition era, I hate my years, yeah. I was the first, I was the first batch. Yeah.
Well, I got doing feeling but got 6 and then GSF
Oh wow.
Okay, thank you for your patience. Back to normal. So we were okay. Someone asked me about exponentiation. So the point of the whole slices now with all the diagrams and the facts and stuff was just to make you understand that when you do exponentiation, it will always be a cycle. It will always be a circle, right? If you don't understand the proof, that's okay. I'm sorry for not making it simpler. But really, I just need you to understand, like, I just really need you to understand that exponentiation will always give you a cycle. It will always go back to 1. So, okay, back to this slide. Hopefully you guys remember this. Phi of m is the number of integers to 1 and co-prime to n. And we did some examples there. So phi of 12 is 4 and phi of 7 is 6. So now this is going to be very this is going to be another proof that we're going to try to make. So let's say that we draw this circle with exponentiation, right? And we have L numbers in this circle. What this means that 1 is equal to a to the power of L. Because, let me see if I can. Because this is a, right? And now we know a is equal to a to the power of 1. It's a to the power of 2. And if there are L numbers in this circle, that means that 1 must be equal to a to the power of L. Yes?
But isn't L?
Isn't L? No, okay.
Because
This is circle,
0
right?
is 1.
So if you count backwards from A, technically it's also 0. But if you go all the way around, you'll get that it's L, right?
Oh yeah, right.
Is that understandable?
Oh yeah, right, because
Okay, yes. So let's say that we didn't use up all the remainders possible modulo n. So that means that L is smaller than phi of n, right? Because we know that when you exponentiate, all the numbers must be co-prime. And we know that phi of n is the number of co-prime numbers. So if L is smaller than n, that means we always have some leftover numbers, right? So here I only drew 1. So we pick one of these leftover numbers, and I call it k1 here. And now we draw another circle starting with k1, and repeatedly multiply by a. Again, remember how this circle has L numbers. This circle is just every element in this circle multiplied by k. So it shows have L numbers, right? Now, there's this key fact here. This new circle will not overlap with the original circle. I kind of glossed over it, but the reason for this is basically, let's imagine that it overlaps, right? So this cross out, let's say this goes to here, okay. So in this situation, the circles will overlap, right? But is this situation even possible? Because, we talked about A and M being co-prime, right? And just now, we saw the same thing where this one circle has 2 arrows leading to it. That's just not possible, right? Because again, A and M are co-prime. We can divide by A, so you can't have 2 arrows pointing to the same circle. So this means that this new circle must not overlap with the original circle. So now we have 2 circles, both of size L, right? So let's say that if we again have some other number left, like K2, we can just keep drawing circles until we have less than L numbers left, okay? So let's think about how many numbers can be left remaining. So if we try to make another circle by the same way, which is, let's say we start with K2, and we go to A times K2, and we go to A squared times K2, blah, 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 blah. We won't have enough numbers left, because we already said we keep doing this until less than L numbers are left, right? So if we have less than L numbers, we won't have enough numbers to finish a circle, right? We'll need to reuse numbers from pre-existing circles, which again means that this circle must overlap with another previous circle. And I just talked about why this can't happen. If this happened, this means that this number would give you 2 possible numbers when you divide by A, which is bad. This cannot happen, right? Because we chose A and M to be co-prime. So since this type of situation cannot happen, we know that there must be no numbers left. Either you have L numbers left, or you have no numbers left. Because if you had some, like let's say 2 numbers left, you can't make a circle, you have to merge into some other circle, which is not allowed. If you have no numbers left, that means that L must divide phi of M. So L must be a factor of phi of M. Okay? So it's a very abstract argument. So let's try to do the same thing we did just now, right? Let's do it's a good example. Let's try to think about mod 17. Okay, why did that happen? So let's do mod 17, right? Let's take A to be equal to 4, which is co-prime to 17. So 4 multiplied by itself gives you 16, right? And 16 multiplied by 4 is 64, yes. But mod 17, that is a bit of mental math involved. Okay, so 64, the largest multiple of 17 that you can take away is probably 51, which is 3 times 17. So 64 is equal to 3 times 17 plus 3 times 17 plus 13. So 16 multiplied by 4 is 13. And again, just keep doing this. This gives you 52. This should, can anyone verify that 13 times 4 is 1 modulo 4? Sorry, 1 modulo 17. Can you open Python? This is how we check. 13 times 4 modulo 17 as well. Or what? 13 times 4. Okay. 52, right? Yeah, 52. 52 modulo 4. Sorry, modulo 17. So 52 percent sign. Percent sign. Not n sign. Percent. Like this.
Oh, sorry. 1 year.
Yeah, okay.
So,
So now that we've so this is 4 to the power of 1, right? And this is 4 to the power of 2. It's 4 to the power of 3. And 4 to the power of 4 is 1 modulo 17. Which means that 1 times 4 is 4, and it closes a circle, right? So we made one circle here. So for 4, right, we have that L equals to 4. Now what numbers are left? We have a lot of numbers left. So if we try to do this with another number left, say 5, right? Again, 5 times 4 is 20, which is equal to 3, 12, 48, 3 minus.
I didn't ask one.
Okay, so 5 is equal to 5 times 4 to the power of 0, right? And 5 times 4 to the power of 1 is equal to 20, which is equal to 3 mod 17. So again, we've made another circle with length 4. So if you keep doing this, right, you see that every single circle you make has length 4, right? And eventually, you have to have no number left over. I'm too lazy to write it out, but yeah. You can try for yourself and you'll see that it's true. So, what have we learned? We've learned that L must divide phi of m. And just a reminder, L is the size of this circle. So for this circle, L equals to 4, right? And phi of n is the number of numbers that's co-prime to m, between 1 and n. So in this example, phi of 17 is 16, right? And we see that indeed 4 divides 16. Wow. So in general, this must be true. Anyone confused?
All I can say L must divide. I don't want to remember all the other theory. Oh yeah, also someone from the chat saying that he can't hear anything.
You can't hear anything?
I don't yeah. Some guy, not 5 out of 5, I'll probably just tell him to like open captions.
Okay, so we have an argument for why L must divide phi of n, right? So what do you do with this information? Well, if we take L to be the smallest positive integer, such as a to the power of L is equal to 1, this is just an alternative definition for L being the length of the circle, right? Because if you imagine and 1 goes here, right, and this goes all the way around. If you have, this is a to the power of 1. If you have L things in this circle, that means that this must be a to the power of L. So this is an alternative definition for L is size of circle. So what we call this L the multiplicative order, or just order for short, of A modulo M. So with the example just now, 4 and 17, right? You see that 4 forms a circle with length 4, so L is equal to 4. So this means that 4 as order 4 mod 17. Yes. Okay, and we have just proved that L must be a factor of phi of n, right? So this is actually an application of a theorem called Lagrange's theorem, which is a more general statement of this fact that your small circle length must divide the total number of things that you have. If you try to look it up, I'm sorry, but I don't think you'll understand what it says on the Wikipedia page. So just try not to confuse yourself. So this also has an important allegory. So if we think about a to the power of phi of m, right? We know that L must divide phi of n. So we can write phi of n as k times L for k in the integer. But we can also rewrite a to the power of kl as a to the power of L and then to the power of k, right? And we know that from the previous slide, this is true, right? L is a small positive integer such that this holds true, which means that a to the power of L must be equal to 1, and 1 to the power of k is just 1, right? So we have this another theorem called Euler's theorem, which says that a to the power of phi of n is equal to 1 modulo n. Here's an example with m equals to 13. We know that 13 is a prime, so every number from 1 to 12 is equal to 13, so power of n is equal to 12. And here, I'm calculating a to the power of 12 mod 13 for a in range 1 to 12, right? And you can see here, they're all equal to 1 modulo 13. So this is an example, this is a demonstration of Euler's theorem. So everyone following? Anyone lost? Okay, all of you guys look super okay, yes? Power of 12, okay. Power of 12 is used because we know that phi of, okay, it's usually 13. So phi of 13 is 12, right? And I want to demonstrate that Euler's theorem is true. So a to the power of phi m equals to 1 mod n. And here I'm just substituting n equals to 13, right? So since we know this is true, this will give me a to the power of 12 is equal to 1 mod 13. So that's why I'm using the exponent 12. Okay? So you can see that it's true because Python has tightly calculated all of these powers for us. So now let's introduce this phi function for real, right? I didn't really talk about what phi is. Phi is called Euler's totient function. And if you recall what the definition was, it was a number of positive integers between 1 and n that are co-prime to n. So the name for phi is Euler's totient function. You can see down here from the Wikipedia page, there is an equation to calculate phi of n. I'm not going to go through this because it's probably going to make you guys more confused. All you guys need to know is that you can compute phi of n if you have the prime factorization of n. Okay? So, okay, that's the end of all the math. So here's a recap of what we learned so far. For a and m co-prime numbers, the powers of a modulo n form a cycle, right? That was like all the things that are on the slide just now. So powers of a mod m, they form a cycle. And since it's a cycle, we must have a smallest positive integer L such that a to the power of L is equal to 1. This is called the order, right? And this is also the length of a cycle. And we have two theorems here, a simple version of Lagrange's theorem, which says that L must divide phi of m. Okay, this vertical bar means divides, right? So L must divide phi of m for all co-prime a and m. And Euler's totient theorem, which says this. Now, if you recall just now, when I calculated phi of 7, right? One of you guys said that for every prime number, phi of that prime number will always be the prime minus 1. Because every single number from 1 to that prime does not share a factor to that prime, right? So we know that from that, the phi of a prime number must always be equal to p minus 1 or p prime. Yes? So a special case of Euler's torsion theorem, which you might have seen, is called Fermat-Little theorem. And it basically is the same thing as Euler's torsion theorem, but with the modulo, we place a prime number. So since we know phi of p is equal to p minus 1, we have a to the power of p minus 1 is equal to 1 mod p. Okay? Actually, you can see this here as well. 13 is a prime number, right? So 13 minus 1 is 12. So this Fermat's theorem says that any number raised to the power of 12 must be equal to 1 modulo 13. Okay, thank you for making it this far. This is the end of all that math. So let's go back. Okay, anyone not following so far? Anyone confused? Okay, yes, you're good. Okay, great. My brain explode. Okay. Anyone with any concrete questions? Yes? Wait, sorry, I can't hear you. We have that a to the power of 5m is equal to 1 over 2.
Yeah, it's a C. It's real. Oh, it's pronounced. Oh,
So, okay, I know a lot of you probably haven't fully digested this math, right? And so, a frequently asked question will probably be, do we need to understand all of this? Do we need to remember all of this? The answer is no, and you probably just Google them. But my reason for including this is to give you hopefully some intuition for how modular arithmetic works. And some of these results become very important later when you talk about RSA, which is our first crypto system. So even if you don't fully understand, please at least try to remember the names of these things, right? The summary. So the word order, Euler's torsion theorem, and you don't need to know this, right? So just remember Euler's torsion theorem and order, right? So now we will finally be getting off math and moving into cryptography again. Yay! So remember just now, in the very first slide in this section, I said that a good asymmetric crypto system should have a private key that is hard to find by attackers, right? Computationally infeasible was the term I used. But obviously, you want it to be easy to generate, right? Because otherwise, no one will use your crypto system. So how do we make an asymmetric crypto system that has this property, right? So the idea is to use these special class of functions called trapdoor functions. What a trapdoor is you enter a trap and then you can't escape, right? So it's easy to go in one direction, but very hard to go in the other direction. And yeah, so trapdoor functions are easy to compute one direction, but difficult to reverse. And we have two very common trapdoor functions here, integer factorization for large numbers. And okay, we're not covering the discrete logarithm problem anymore, because everyone's confused, so just ignore this. So one very commonly used trapdoor function is integer factorization. Now, I don't know if you guys heard, but you guys know about quantum computers and Shor's algorithm, right? Shor's algorithm is a quantum algorithm that factorizes large numbers. And why it's such big of a deal is because factoring numbers for normal computers is very hard, especially for big numbers with big factors, right? So let's see how we can use this factorization problem to make a secure crypto system. So let's talk about RSA now. So here's a setup for RSA. Let P and Q be two large primes. You define N to be the product of P and Q. Let E be a prime number, which is most of the time 65537. And we want to encrypt messages, right? Obviously. Otherwise, what's the point of having RSA? So to encrypt the message, we first represent it as the number N. So as we already said just now, we can represent strings, bytes, as numbers, right? So you first represent your message as number n. Then your ciphertext will be m to the power of e modulo n. Okay, that's it. It's that simple. So now you know how to encrypt messages under RSA. But how do you decrypt messages, right? There's no point in encrypting messages if you can't recover a message. Yeah, this is an example. So I'm using the function getPrime from PyCryptoZone, which basically gives you a prime, right? And I imported bytes long like just now. So here I define the primes, I define e, I calculate n is this giant number. And I have my message, which is hello colon 3. And the message was converted to a number is this 75225, blah, blah, blah. And remember, encryption is d equals m to the power of e modulo n, right? So I calculate, okay, the Python power function, when you use 3 arguments, is calculates n to the power of e modulo n, okay? And we get that the ciphertext is this string of numbers. So this is an example of how to encrypt messages in RSA. How do we decrypt messages? So from school, you might have learned that this holds true, right? This is like a basic law of exponentiation. This also holds true over modulo, which we used just now. So we have a number c such that c is equal to f to the power of e mod n, right? And we don't know what m is, we do know what e is. So ideally, we want to find a number d such that c, when raised to the power of d, gives you back the original message, which means this is true, right? This means that m to the power of e times d is equal to m, modulo n, modulo n, sorry. So I can construct such a d. So to decrypt RSA, you want to be able to construct such a number d such that it undoes your encryption. Remember Euler's torsion theorem? Yeah, this is the application part. So by Euler's torsion theorem, we have that n to the power of 5n is equal to 1 modulo n, right? So remember here, we want this to be true. But since this is true, we have m5n times med is equal to 1 times med, which is equal to med, right? So we have that if you have med and you add or subtract integer multiples of 5n, the answer won't change. You'll still get the same value. So we want to find d so that this is true. Okay? So if you notice here, right, we have this thing about adding multiples and subtracting multiples of 5n. Doesn't this sound awfully familiar like modular arithmetic? So what we can do here is, because we can treat exponents differing by a multiple of 5n as essentially the same, we can set up a new congruence, right? We know that ed must be equal to 1 modulo 5 of n. Does that make sense? Any questions? What? Okay. So again, our goal here is to find a number d such that m to the power of e times d will be equal to n. That means I'm decrypting my message encrypted by RSA, right? And from all the math just now, we know that this is true. This is Euler's torsion function, right? As a consequence of this, if I multiply this and my m to the power of ed, I'll get m to the power of ed back, right? And if I multiply again, I'll just get m to the power of ed again, because this is equal to 1, and 1 times anything is equal to the thing. So we have this m to the power of ed plus k times phi n will be equal back to m for any integer k. Yes? Do you understand? Okay, hopefully. So now that we notice that we can treat exponents that differ by a multiple of r of n as essentially the same. This is what we were doing with modulus now, right? Because if you remember, under mod, let's say mod 5, right? You have that 0 is equivalent to 5, equal to 10, so on. 1 is equivalent to 6, equivalent to 11, and so on, right? Here, we're treating numbers that differ by a multiple of 5 as essentially the same. And by analogy, here we're treating exponents differing by a multiple of 5 as essentially the same, right? So if we know that this is true for the value of d we're trying to find, this will also be true, right? This will be true for some value of d and k. And now since we know that e d times a multiple of 5 is equal to 1, this can be rewritten as ed is equivalent to 1 modulo n. This is like a key step that I'm hoping you guys can understand. Okay, everyone, is everyone clear? Any questions? Okay, I'm just going to assume that you guys all understand. So yeah, just a reminder, we're trying to solve for d given e and n so we can encrypt our we can decrypt our ciphertext. So now that we know e times d is equal to 1, right? How do we find d? Oh yeah, okay. So notice that this modulo holds true under phi of n, right? So what is this phi of n? So this was a screenshot I used just now, the definition of phi from Euler's social function from Wikipedia. And you see here that this is an equivalent formulation, right? And we know that n, as we defined it, is equal to pq with p and q prime. Yes? So here we have n equals pq, right? Which means that I of n is equal to p times 1 minus 1 times p minus 1, q times 1 minus 1, q minus 1. Okay, this is just plugging the prime factorization into the formula, okay? Now, we know that 1 minus 1 is 0, right? Any number raised to the power of 0 is just 1. So, we have that phi of n is equal to p minus 1 times q minus 1, okay? Everyone understands? Okay. So now that we know what phi of n is, right, we can divide by e on both sides of ed equals to 1. And again, this is possible to do. Remember how previously we talked about, if you're dividing by a number that's not co-prime, you'll run into issues, right? But here, e is prime, so it's automatically co-prime to every single number except the modules of e. So we won't have any issue with division, right? So if we want to calculate d, since ed is equal to 1, d is just equal to 1 divided by e, which is the inverse of e mod phi n, right? And now, we know what phi of n is. We can calculate it with our formula here just now. We also know what e is, because we chose the value of e to be 6.537. So obviously, we can calculate d, right? So we have the value of d, so we can decrypt our ciphertext. Wow. So, as a reminder, this is our ciphertext, right? Sorry, not d. This is our ciphertext. If you raise m to the power of e to d again, you get m to the power of e times d, right? This is equal to 1. Because we specifically chose d such that e times d will be equal to 1 mod phi n. And we know that when you're working with this exponent, right, exponents differing by a multiple of phi n are essentially the same. So this means that ed is equal to 1 plus k phi n for an integer k, right? This is the definition of equivalent under modulo. So if we look at m_ed, this will be equal to m1 plus k phi n, which will be equal to m times m raised to the power of 5 of n to the power of k, right? And from Euler's quotient theorem, we know this is 1. So this is equal to m times 1 to the power of k, which is n, right? So this is like all the steps are skipped in this equal sign theorem. So we raise the ciphertext to the power of d modulo n to decrypt our message, okay? So coming back to our definition of asymmetric, the public key then is n and e because we use this to encrypt messages. And the private key is d because we use it to decrypt messages, right? So that's the RSA cryptosecret.
Yeah.
And here's an example of decrypting, right? Like we said earlier, phi is equal to p minus 1 times q minus 1, right? And d is equal to the inverse of 1 divided by e, right? Which is just the same as the inverse because, yeah, division is same as multiplication by the inverse. And this is a continuation of the Python screenshot from earlier. So if you raise our crypto, if our ciphertext C is part of D mod N, we can get back our original message. Yay! So why is RSA secure, right? If it wasn't secure, no one would be using it. So remember, when we were trying to find D, right, we needed to calculate the value of phi of n. And if we know the factorization of n, this is simple. We just use a formula in Wikipedia. But let's say we don't know the factorization of n. If I just gave you, let's just say, I gave you this long number, right? 1391965 blah blah blah. You probably couldn't factor it by hand. If you ask the computer definitely can do it for you. That's because this is too short. But for longer numbers, for larger numbers, factorizing n will become harder, right? So if we can't factorize n, this means that we can't find phi of n, right? Because we don't have the prime factorization to plug it into that neat little formula just now. If we can't find phi of n, that means we can't find d, right? Because we don't know what. Because for this, right, we don't know what phi is. So we just can't do it. So if you can't find d, that means finally you can't decrypt, right? Because to decrypt, you need to know the value of d. So this means that for an attacker, if they only know the public key, right? Since only the public key is made public, if an attacker only knows the values n and e, it's computationally infeasible for them to find d. Because to find d, you need to factor n, and factoring large numbers is hard. So this is where the security of the RSA crypto system comes from. Yes. So in actual applications, the example in Python that like this slide and this slide shows, it's just like a toy example, right? So in actual applications, you don't actually generate your own primes and use them, right? You use existing software that other people built to generate your primes, generate your n and your e, and to encrypt your messages. And there are certain considerations that you need to take before you can actually encrypt the messages. So the actual encryption process is the actual process of you raising f to the power of e is abstracted away. You just call, the function encrypt, and encrypts the messages for you. So now we come to this famous adage. It says, don't roll your own crypto. What it means is, don't try to implement your own crypto system. Because there's so many things that can go wrong, so many things that go awry, right? And just as a short list, here are some things that can go wrong. So let's say you're choosing your own primes, right? And you say, I want my primes to be close to each other for some reason. That's not safe, because if you choose, let's say P and Q, right? And we have that P is equal to Q plus 2. So if we do N equals to PQ, we know that this will also be equal to Q plus 2 times Q, right? So if you use some, if you think about it, this is actually Q plus 1 times Q plus 1 minus 1, right? Now you might find this expression familiar. This is a sum multiplied by a difference. So it's a difference of 2 squares. So this is actually equal to Q plus 1 squared minus 1, right?
It's Q plus 2Q.
Sorry? So if you choose your numbers P and Q such as they're too close to each other, and this holds true, if I'm trying to factorize n, I don't need to try to factor it, right? I can just add 1, take the square root, and minus 1 to get back one of your primes. And actually, you don't need it to be a difference of 2. You just need them to be close enough. So, okay, we're going to go back to math here, right? Let's say that P is equal to Q plus 2K, right? And K is a small number because your P and Q are very close to each other. Now, if you consider this, you have that this is equal to, can I erase on this thing? Oh, I can, okay. So P equals to Q plus 2K, right? And N equals, okay, where K is small. Oops. N equals to PQ, which is equal to Q plus 2K times Q, right? We can do the same trick as earlier. This is Q plus K plus K, and Q minus K, sorry, Q plus K minus K, which is equal to Q, oh my god. Okay, I'll just work like this. Q plus K squared minus K squared, right? And we know K is a small number. So what we can do is, we can take your N, we repeatedly add small squares. Let's say N plus 1, N plus 4, N plus 9, right? If K is small enough, eventually we will add back the K squared. So let's say that K equals to 4, right? So that means that P will equal to Q plus 8. So if we try to find N plus 16, this will be equal to Q plus 4 squared. And now we can just trivially take the square root and minus 4 to get back on our primes, yes? So the point is that if you choose your primes too close to each other, you can just do this, you can just try adding squares. If it's a square number, you take the square root and you subtract that number to get back on the primes. So if your primes are too close to each other, this crypto system is actually not secure, right? And now, if you reuse your primes, it's actually also not secure. Because let's say we have N equals to PQ, like N1 is equals to PQ, and N2 equals to QR. So we're using the same prime Q in two different places, right? And now, if an attacker has access to both of these moduli, they can just pick the GCD, right? Because the GCD is an easy function to compute. And we do have a common factor here, which is Q. So if you take GCD, if we take the GCD of N1 and N2, we will have trivially recovered Q without needing to factorize any of the moduluses, right? So that's also one of the common pitfalls of trying to implement your own RSA. Another way you could give an attack information is if you leak information on your own, right? Let's say, I don't know, you use some biased random number generator, so your primes have a bias in them. Let's say that they tend to be close to a certain number. Then you could just use that information, construct like an equation, solve it to find P and Q. And there's more ways, such as if you choose E as a really small number, let's say E equals to 3, right? Okay, let's say if we choose E equals to 3, 3 is a very small number. Like, when you cube a number, it doesn't actually go up that much, as opposed to if you raise it to the power of 65537, right? So let's say I have this message 3, right? And let's say my N is P times Q, and it's a very big number. Let's say it's about 2 to the power of 1024, okay? And let's say my message is very small, only like about 3 characters or so, right? So we know that each character in a message is 1 byte, which is 8 bits. So we know that our N is approximately on the order of 2 to the power of 8 times 3 for 3 character message. Okay, now let's think about what happens if we try to encrypt this message N with E equals to 3 with this giant modulo, right? If we do M to the power of E, we know this is approximately equal to 2 to the power of 8 to the power of 3, which is equal to 2 to the power of 24, right? Uh-oh, our exponent, our modulus here is to the power of 1034. So we don't actually make use of the modulus. We only end up with a ciphertext that's smaller than the modulus, which means that the modulus doesn't do its thing. This is the same as if you just exponentiate it normally over the integers, right? So if you happen to use a small e and your message is small and your n is too big, what you can do is, if I have m to the power of e, right, and we know this is equal to 3, it's n to the power of 3. We get this c equals to m to the power of 3. What do? Oh, I can just take a cube root, right? Because if I just take the cube root, we know that the modulus didn't actually do anything. It might as well not be there. So if you take the cube root, you can trivially recover your original message. And there's a lot of other ways to do RSA wrongly, which is, let's say you have related messages, right? You can actually set up another system of equations and solve for that. If you had your messages badly, again, you're leaking extra information with that. And so these are all actually very common in not beginner, let's just say medium difficulty RSA challenges. So demo time, okay. So let's say, oh my god, how do I use the Mac? Somehow, how do you zoom in on this thing? Oh. Okay, hopefully this is legible enough. A bit bigger. Okay. So again, we're coming back to Python to demonstrate RSA, right? And we want to be able to generate prime. So let me just import that real quick. Okay, so now again we generate 2 primes. So it's equal to get prime. The argument here is how large you want the prime to be. So 256 means that you want the prime to be 256 bits big, which is big enough for our applications. And this is cube, right? If we do e equals to 655. Okay. So now, if we were an attacker, right, all we would have is the value of n and e. We don't have the values of p and q. They're hidden from us, right? But let's say now somehow we manage to get the value of 1 prime, right? Let's say we know what p is now. Wow. So how do we decrypt the message? Let me just encrypt the message real quick. And let's say our message is hello from Ohio. So to encrypt this message, again, we'll first convert it to a number with bytes too long. This gives us a number, right? This number represents this message. And then we'll calculate n to the power of e modulo n. So this is our ciphertext, right? Oh yeah. Okay, yes. Yeah, you guys won't get the same value when you try doing it yourself because p and q are random primes. So yeah. So let's say that now, okay, I encrypt this message and now I'm an attacker. I'm trying to break our secret system. If I only had information n, e, in this message, it would be the ciphertext. It would be really hard for me to find out what the original message is, right? Because I can't factor n in my head. I can probably ask a computer to do it, but we're using small primes for demonstration. So n is essentially unfactorizable. And so we don't know how to decrypt. We don't know how to decrypt C. We can't see the message. But now let's say someone tips us off and we learn the value of one of the primes, p, right? So if we had p, if you had a value of p, how would you go about decrypting the message? Okay. This is a question that I'll ask somebody again. Who's a good? How about you in the orange shirt? Yes. So let's say I have this RSA crypto system with n, e, and a message and a ciphertext c, and I know one of the values of p, right? How do you think we can decrypt this message? Okay, you're right in saying that we need to find the other prime number, right? But we don't actually need to use brute force. Because we know that n is equal to p times q, right? We have the value of p, we have the value of n. So if we just do n divided by p, we should recover the other prime trivially, right? Okay. Yeah. So you see that if we have one prime, we can recover the other primes by dividing n with p, right? So now we have both primes. Now what do we do? Ask another person. White shirt, you at the back. What do you think if you continue from here? Divide what? Okay, that was the previous step. So now we have obtained the prime. What do you think we should do? This is the slides. Okay, so if you go back to the slides, right, you'll see that to decrypt an RSA ciphertext, we need to know, first we need to calculate what phi of n is, right? So we can do that here. Again, phi of n with the formula is equal to p minus 1 times q. P minus 1 times q minus 1. Yes? And then we want to calculate d, which is the power that we will raise our ciphertext to. We try to decrypt the message. And we know that d is equal to 1 divided by e modulo phi, right? So the way we do that is d equals to e minus 1 phi. So now we have our value of d. Very good. So now, from one league of the prime, right? Remember, we are only given one extra number, which is not the primes. And now we got all of these extra information, right? Now that we have d, we can finally decrypt our message. So that's, if you remember, that's you raise our ciphertext to the power of d. And that gives you a small number back, right? And if you actually do long 2 bytes with that small number, okay, underscore just means previous value. So, yeah. So if you convert this number back in bytes, you'll get our original message. So this is a demonstration of how just even knowing one prime can ruin your whole security, ruin your whole crypto system. Okay, I think you guys are trying it out on your own computers, so if you encounter any issues, you just raise up your hand. Yes. I think everyone should be about done. Yeah. Okay, now I'll give you guys like 2 more minutes. You guys can try it.
So that's agree? 2 hours and 36 minutes, I officially give it up. So how do you do this? I don't care about the next. See, I'm using Ubuntu. There's a normal one is dollar sign. The normal one is see, there's like dollar sign. For me, mine has double arrow. Yeah, but not arrow. This is I'm using Ubuntu, but we won't have to do this. So should work. Wait, I have screenshots. And, just follow mine word for word, edit your strings. Why are my files doing dance? What do you do? Oh yeah. Screenshots. No, my files are doing dance. No, I'm having a problem. Just because like all of that weird math, my files have started going crazy. It's not even me. I wish it was yes. Finally, also M double divided.
Okay, just some common questions that you have asked before. Okay, question number 1. Why is E chosen to be 6.537? It's a number that's convenient for us because 65367 is a number such that when you try to exponentiate by it, it's more efficient to exponentiate than like any other number. And it also has some other properties that make it a bit more secure. Like first of all, it's big enough, and yeah. Secondly, what is this B thing before the string, right? Like what is it just now? The B just shows that it's a byte string. The actual distinction between the byte string and the string isn't important as of now. But we're using a byte string here because the functions that convert a string to a number and a number back to a string take in bytes. So that's why. For the original message, we have a B in front of the string. And for our decrypted message, we just have a B in front of the string.
Clarify. This E was basically for already. Sorry, we get a bit of help with this guy. It's stuck on he got stuck on the important something a bit so weird.
Hello, okay, so in the training announcements in the Discord, you may find sample code for implementing RSA. Feel free to reference those as you are following on experiments. And if anyone is stuck with the demo, do raise your hands and we can get to you guys shortly.
So yeah, I think installation. Yeah, no, because you just type. No, I did everything. No, get prime. If you do that, you have to do like crypto util number, get prime. No, but why not import? Because you import all those A logs, like you just need those two things. And C, it's easier if you just use get prime. Like later you crypto util number, get prime. You have to type even more. Like this before.
Oh, then you just use n divided by 2 to get 2.
No, you have to import first, all the way to the top.
You already imported that. The thing is that E is a variable that is defined, then a variable is like only import variable.
Oh yeah, you must equal something. Oh, I thought this error was sorry.
Yeah, because
E must wait. When you use equals, you clone a variable. You need to take the letter and then you assign it a value. Yes, you define it. So equals is the defining value. So E equals, and the example it says 65537 is the value. So every time you press now, it shows. Yes. E comma Q equals, as you can see, right? This means you're going to assign 2 at one time. E comma Q equals, then use get prime brackets 256. Comma get prime 256. That one you did like earlier, at the start of this whole thing.
So we're using some right. Let's use this in this case, because we know that so we know that so it's fine if we use
No, you see, it's like exactly.
Sharp 57.
Yeah, and then I asked this, you want to put positive like this? See what the actually
okay, there's other ways.
imagine it doesn't really
It'll be hilarious if you just after like 5 hours you just stare at it, but it's just
yeah, that's like a simplest way. It's just to preserve Okay, sorry for that complicated math explanation. Luckily, it's lunchtime now. So as with yesterday, we'll be doing flow control. So first 2 rows, please queue out in front, collect your lunch.
generate.
Oh wait,
down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Systems down. Enemy detected. A silent cyber parasite is spreading. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Systems down. Enemy detected. A silent cyber parasite is spreading. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Systems down. Enemy detected. A silent cyber parasite is spreading. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Systems down. Enemy detected. A silent cyber parasite is spreading. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Systems down. Enemy detected. A silent cyber parasite is spreading. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Systems down. Enemy detected. A silent cyber parasite is spreading. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Systems down. Enemy detected. A silent cyber parasite is spreading. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Systems down. Enemy detected. A silent cyber parasite is spreading. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Systems down. Enemy detected. A silent cyber parasite is spreading. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Systems down. Enemy detected. A silent cyber parasite is spreading. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Systems down. Enemy detected. A silent cyber parasite is spreading. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Systems down. Enemy detected. A silent cyber parasite is spreading. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Systems down. Enemy detected. A silent cyber parasite is spreading. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Systems down. Enemy detected. A silent cyber parasite is spreading. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Systems down. Enemy detected. A silent cyber parasite is spreading. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Systems down. Enemy detected. A silent cyber parasite is spreading. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Systems down. Enemy detected. A silent cyber parasite is spreading. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Systems down. Enemy detected. A silent cyber parasite is spreading. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core. Hunt it down fast. Be rewarded with up to $30,000. You in? Every keystroke counts. Every second matters. It's a race to the core.
I mean, they're not wrong. My top three is Nanyang for all three IDs. Because I think
Hey everyone. Okay, everyone, we'll be resuming with our workshop on symmetric topology. So,
But this guy never thought about why you
okay, so can everyone just like sort of like pay attention? The mic is like off battery currently, and just wake up your neighbors if they are fallen asleep. Yeah. Okay, the mic doesn't seem okay. All right. Okay, so we'll be looking at symmetric topology and okay, perfect. Hold on. Alright, so before we move on to covering crypto systems in symmetric applications, we must first consider the idea of so we must first consider those at the back, can you guys hear me if I'm like talking this loud? Okay, perfect. So we must first cover the concept of functions. So functions are essentially an assignment of elements in one set or one group to elements in another group. So in this example here, in the diagram on the right, we have a function f that's mapping elements from A to elements in B. So here A1 is mapped to B1, A2 to B3, so on and so forth. And the function is responsible for the mapping. So for general intuition, just consider functions as some like match or some like transformation that's happening. So a simple function, like if you want to go into numbers and math, we have fx is 3x plus 7. Then 1 is mapped to 10, 2 is mapped to 13. U in the ratio in the front row, 1 or 3 mapped to
16.
Yeah, 16. Yes, correct. Good job. Yeah. And at the same time, functions can take in multiple inputs. So for example, I can have a function that takes in an item or a message like x. I can take in a key like k. And then in this example, this function is taking x and k and is doing f equals to kx plus k. So if my key is like 1, 2, 3, and I keep it as that same value, 1 and 1, 2, 3 is mapped to 2, 4, 6. 2 and 1, 2, 3 is mapped to 369. And yeah, so let me arrow my first. You guy in the purple sweater, right? Yeah, second row. That's yeah. What does 0, 1, 2, 3 map to? Correct. Yeah, 0, 1, 2, 3 map to 1, 2, 3. Okay. Okay, the mic is working. Good. So now that we've gone through some intuition about functions, it's time to go through what a symmetric crypto system means. So a symmetric crypto system essentially contains one private key K. So Azizo did mention this, but in asymmetric crypto systems, we have a public key and a private key. In this case, we are just looking at one private key, and we have this key and a function that does something to a message M with the key. So essentially, the crypto system is just some function that takes in a message and a key, and it outputs a ciphertext. So unless you have the key, then you cannot really recover the original message. And without the key, it will be difficult to reverse it. So in symmetric crypto systems, this key value or K is static, meaning it's a constant value, and it's secret, meaning that only those who are supposed to receive the message will know the key. M is what we call our plain text or our message, and C is our ciphertext. So ciphertext is essentially our encrypted message that we will put out there for people to decrypt. So symmetric crypto systems are there to answer the problems of confidentiality and integrity, mainly that only participants with the key can decrypt the message, and if the message is altered, the decrypted output will look gibberish, because in the sense that the moment I change my M or I change my K, ideally I want it to be such that the output will be like messy, so people can tell that oh, the message has been tampered with. So in order to establish a good symmetric crypto system with the form like FMK equals C, we generally use two ideas that we call diffusion and confusion. We will be going through what these mean in the later slides. But for now, we'll consider the very basic mapping of F, which takes in M and K, and just returns M. So what this means is that if our plain text is 110, 11010, we call data representation, then our ciphertext is 110, 11010. So far, it gets from this? Okay. So the problem now is that if we change one bit of our plain text. So recall that was a 1. If you change it to a 0, right? Can someone tell me where the ciphertext with the change be reflected in? Yes. This one?
Fourth one.
Or the fourth one? Are you sure? Okay, correct. Only this one is being changed. This is very insecure because if I change one small element of the message and everything in the ciphertext is changed very little, it is kind of quite insecure because, okay, there are reasons why it's insecure, but we call this weak diffusion. It's weak diffusion because when I change a small amount of my message, the change in the ciphertext is very small. We actually don't want this. We want something that's complicated, something that is very complex, whereby any small change in the plain text will cause big changes in the ciphertext in general. That way, it will be very hard for the attacker to, given a ciphertext, find a way to reverse to recover the plain text. And before we can talk about making things hard, we must consider a certain operation that is called the bitwise XOR operation. The XOR operation is essentially a logic operation that occurs between 2 bits. So the general idea is that if A and B, which you can see in the top right, they are like inputs into a gate that's a XOR gate and outputs as Q. If A and B are the same, so if A is 0 and B is 0, or if A is 1 and B is 1, Q will be 0 because they're the same. But if A and B are different, then Q will be a 1. So like 0, 1 is a 1, 1, 0 is a 1. Yeah, so we are going to do a exercise. So let's say I have A that is 11001 and a B that is 01011. Can someone yell out what this first part of A or B will be? 1 or 0? Yeah, it's a 1, and then the next one is a correct, and then a 0, and yes, alright, good job guys. So now that we have gone through the basics of XOR, it is time to go through. Okay, the slides have crashed again. Alright, so now we can start going through properties of XOR. So earlier we were looking at XOR with binary strings or bit strings. Now we're looking at XORs across numbers. So there isn't really much of a difference, it's that it's just converting numbers to binary, storing them in binary, and then reconverting them back to decimal. But there are a few properties that we can look out for. So the first is, if A XOR B is C, then C XOR A is B, and C XOR B is A. Basically, I can take any value in the left-hand side, I can switch it over to the right-hand side, and it will still be the same. So in our example, we have 2671, XOR with 1908 is 3355. Therefore, 3355 XOR with 2671 will return the other number. The other property is that any number XOR with itself will be 0. So it kind of cancels each other out. So like 12345, XOR with 12345 will be 0. And similarly, any number XOR with 0 is itself. So 12345 XOR with 0 is 12345. And these are basically the general properties of XOR, and you can do very interesting things with it. Like for example, you have A's or B's or C's or B's or A. The B is XOR with B, so this cancels out. The A is XOR with A, so it kind of cancels out. So you're left with C. So you can kind of see this in the demonstrations here where A's or B's or 1, 2, 3, 4, so A's or B is C. It doesn't matter where my A is. My A can be like here or here. As long as two of them appear the same thing, they will cancel out.
And then 0 XOR C itself, so
Alright.
that's why A, B, C, D, A.
So for those who are trying to emulate this in Python, the caret sign is basically the XOR operation. So if you go to Python and you do like 1 XOR with 2, you will get something like 3, and 3 XOR 2 will be 1 if you were to do it in Python directly. So before we move on, I'm going to make sure that everyone understands what this means. So I'm going to do a quick fire round, okay? Okay, I'm going to go to this side, so like this whole left-hand side. I'm sorry, you guys are selected for questioning. So I'll go one by one, and then you can just answer the questions, okay? what is A XOR, okay, so let's say A XOR B is C, okay. What is C XOR with B? C XOR with B is A. Okay, what is A XOR with A? Right, 0. Okay. What is A XOR with B XOR with A?
A XOR
A XOR with B XOR with A.
Yes. Remember? Yeah, because
Yes, A XOR with B XOR with A is B because the two A's together twice cancel out.
so the A,
Now on to you. What is B XOR with B?
and you just get C XOR 0.
Yes, B XOR B is 0. Okay. What is A XOR with A XOR with
Yeah,
A?
anything XOR itself.
Are you sure? What do you think is A?
Yeah, anything. As I said, A is right. A is just plugging
Correct.
number.
So if something appears in the XOR an odd number of times, then it won't be cancelled out. But if it's an even number of times, it will cancel out. Right. Next question. What is A XOR B XOR C XOR B XOR A? Correct, C. Okay. What is B XOR B XOR C? Correct. Right. What is B XOR C? Correct. Okay. Alright, so far, before I move on, does anyone have any questions that you would like to ask?
Yeah, you still have a zero because the C is all 0 is all 0 is still C.
Yes,
We
correct.
still have a value, but
Zero is like an
but yeah, I can still say cancel lah. Cannot use minus in the server. Because 33575 XOR 2671 is not 3355 minus. Otherwise, it would be like at least the last entry before. That's all I can say, right? This off the top of my head, but so it's not minus. It just yeah, because you have to expand them into units.
Yeah.
And yeah. What is this?
There's another term for XOR called carrier addition. I'll let you figure out what that means.
I don't know as a guy who actually learns home computing because I only learned XOR as in like just a logic gate, the ORs and the ANDs. I didn't do XOR with numbers.
The idea for XOR is that you're doing addition at every bit, but you don't carry over to the next bit. So it's carrierless addition. Because like 1 plus 1 is 1, 0, right?
Oh yeah.
You take a 0, you don't carry over. Yeah.
That one you don't need honestly. That one too cheap.
Alright, so far so good? Okay.
Oh my god.
Now that we're done with XOR, I'm going to introduce you all to a shift operation. We will call this SF because shift has S and F. But the general idea is that if I want to call shift operation, taking in M, which is 1101010, and I shift it with 3, I'm basically taking the entire thing and I'm just moving to the right by 3 bits. So the one in red is moved 1, 2, 3. So it's moved here. And similarly, the green one is moved over here. And for the purple one, we kind of like move it to the right, then we wrap back around to the other side and we move it back here. There is another term for this operation, we call it right rotate, but don't worry about it, we won't have to figure out what right rotate means. For now, just take it as it is, just an operation that shifts everything to the right by the amount that is provided. So far so good? Oh, so like here, right, shift is shift M with 3. So 3 means we take everything and we move it to the right by 3 times. So like we move 1 3 times here.
And then the ones that are already like closer to the right, they get stuck through a magical portal and all on the left side.
Yes, correct. The ones on the right are stuck through a magical portal and come on the right side. Come on the left side. Alright, so we are going to put those two together with our new function that takes in m and exhausts it with the shift right of m with 3. So I've already given the binary form of SFM in 3, and the arrow is there to help reinforce our understanding. Alright, can someone tell me what the missing numbers in the ciphertext are? The answer is 0, 0, and 1, by the way. The idea comes from using the XOR gate. So like 1 XOR 0 is 1. 1 and 1 are the same, so it's 0. Similar reason, this is 0, this is 0, this is 0. And then the last one is a 0 and a 1. Those are different, so you put 1 at the bottom.
So this is also kind of because you need
And now, if you notice now, when I change one bit in m, can someone tell me which value in SFM3 is going to be changed as well? Which position? So if I change the 1 in m over here on the top index to a 0, right? Where in SFM3 will this be changed? Second last one, right? Indeed. The second last one will be changed because I shifted it twice. And now, here's where the magic happens. When I saw them together, two values are being changed.
And therefore it gets more confusing.
No, it's diffusion.
And yes, and yes, I think.
And now I'm confused as to why the blue different cards are working.
So it makes things harder for people, which is the whole point since you're making things secret.
And now, if I want to do something funny and I start putting multiple SFs inside, you can see in the bottom here, I don't know if it's large enough, but this is an implementation of the shift right function, and I'm just doing the same thing over and over again. You will notice that when I change one bit in anywhere, and the bottom is just Python code for to reference it, 4 bits are changed. Okay, quick question. Why would 4 bits be changed here? Yes. So it changes 4 bits. Yeah, that's more or less the right idea. So this is what we call strong diffusion. Wow. Yeah. So weak diffusion is when changing one value in M changes only one value in the ciphertext. Now, when we change one value in our message, almost half of our ciphertext is being changed. So an attacker facing this may find it a lot harder to find differences in message and how it will affect the ciphertext, because the ciphertext will change dramatically. So if you want to know the Wikipedia definition, I'll get to whoever raised their hand later. Diffusion means that if you change a single bit of the plaintext, half the bits in the ciphertext should change. So this is what we're looking for in a perfect block cipher that's secure. Before I move on to the next concept of confusion, is anyone confused? Yes, you. What question? Sorry? Oh no.
Yeah.
So the shifting itself happens under the hood, but when you run it, the ciphertext itself is this. So you know that 4 of the bits are being changed here. So the original bit is changed, the original bit shifted 3 times is changed, the original bit shifted 1 time is changed, the original bit shifted 5 times is changed.
I know, but like the math I'm talking about is just those complex. I don't want those theorems.
Does anyone have any other questions?
Like, yeah.
without any ado, we will move on to the next topic, which is, okay, so, while the function here has strong diffusion, because when I change one bit of m, almost half of the output is changed, it is not necessarily secure. Because given any output, anyone can actually reverse the function to recover the original message. I would recommend you to try reversing this function, but I'll let you know that it is not very trivial. But the thing is, because this function only uses a message, it doesn't use the key at all. So what's the point of using a key if we're not going to use it in our block cipher? Therefore, we need to use a secret key k. It's a key, so it can be any key. So now let's say we use the key. So we're going to do m resolve with k. That way we use m, we use k. This has weak diffusion, but it's okay, we won't consider diffusion for now. So here, m is 100, 110, and k is 10111001. The ciphertext, which is the XOR output of both values, will be 00101011. I think so far everyone can understand this now. So, when I change one bit here in k to 0, what will happen to the ciphertext?
The ciphertext
Ciphertext will change, but where?
the same digit.
Correct, same digit below the 0, so it will change to a 1, right? Indeed, it changed to a 1. But then, now, I changed the key by a little bit, ciphertext only changed by a little bit. So, this is what we call weak confusion. And there's a way to attack crypto systems that has very weak confusion, but we will not cover it within the scope of this workshop for now. I do invite you all to basically try and think of it in your head, and just find ways to break ciphers with weak confusion. So, how can we make it more confusing? Don't we all love to be confused? So, let's say we bring back our SF, and we do SF m resolve with k, shift right 3, and resolve with k. So, this is very hard to visualize in your mind. So, we use Python to basically replicate it using a a function definition to return SF m resolve k with 3 resolve back with k. And when we now run it through, we see that when we change the k by 1, and we do the same change, the ciphertext, 2 of the values will be changed now. And when we chain a bunch of them together, like so, like whatever the heck the top part is, when I change the k bit by 1, 4 bits in the ciphertext are being changed. And if you want to visualize this, you can think of it as the shift function doing the heavy lifting, making sure that each key bit is being used to resolve a different message bit every single time. Because of that, changing one key bit will affect 4 different message bits that will be outputted, because this one key bit is used to resolve multiple message bits. We call this strong confusion, because changing the key changes the ciphertext by a lot. And yeah, I'll pause this for a moment so you guys can follow the logic first.
Okay, so you saw it with k. You shift it 3 times. You saw it with k, which makes the whole, which makes the result of the second shift even more weird. And then you shift, it again, and then because although the k has stayed the same, the shifting has caused it to be more predictable and therefore strong confusion.
So actually, if you think about it, this function not just has strong confusion, but there's strong diffusion as well.
Because you shifted.
Yes, because of the shifter. Actually, wait, no. I don't think it has diffusion. No, I changed the message bit. You only changed one of them. Yeah. No, this has weak diffusion but strong confusion. I won't explain why. I'll leave you all to figure it out.
Is there like a function that can have both strong diffusion and strong confusion?
There are functions that can give strong diffusion and strong confusion. We'll be looking at one of them later on. Yes, the concepts are involved in it, yes. So, when you think about it the reverse way, much like how changing one key bit changes the ciphertext, one ciphertext bit can be changed by modifying multiple key bits. So if you change any of these key bits, you can actually change the ciphertext now. Yeah. And this is what we call confusion, where every bit of the ciphertext depends on several parts of the key. So this is just meant to obscure connection and to hide the relationship between ciphertext and key. Therefore, it is very difficult to, given a plain text and a ciphertext, figure out the key. This makes it more ambiguous. And with diffusion and confusion, whereby changing any message or key bit lead to huge changes to the ciphertext, without knowing the key or the original message, given any ciphertext key, it is actually very, very hard to recover it. You would have to brood over all possible k values and look at all possible m outputs to figure out which one would be the right plain text. And the range of key is called the key space. So like something space means like all possible values you can take. So, and only one value of k would exist where decrypting multiple ciphertexts yield valid and readable plain text. But finding this value is quite hard because you have to kind of like brute through everything. And when my key space is very large, it's even harder to break this triple system. So, as someone may have asked, what function do we have that has strong diffusion and strong confusion? We figure this out by going to block ciphers first. Alright, so suppose we have a very strong diffusion and strong confusion function f. We don't have to worry about what f is, we'll figure out what f is later on. Let's imagine that we already have a function that does this. How shall we use it? We recall that the difficulty of breaking a function that has strong diffusion and confusion is how big the key space or the plain text space is. So if our key is very large, so if the key has a lot more possible values, it is a lot harder or more difficult to break the system. But then this itself invites problems. First off, how can we encrypt plain text with different lengths? And secondly, if our key size or plain text size is too big, to encrypt a single message will take more and more time. Because if my key is like millions of bytes long, I will need a million more times to encrypt a message that's just 1 byte. So we need to standardize this. And we also need to figure out how to deal with plain text of different sizes as well. Therefore, our solution is we fix what we call a block size, which we refer to as BLKSE. So the block size can be something like 16 bytes, which is just 16 characters, which is also 128 bits long, because 16 times 8 is 128. Regardless, we can pick something like say 16 characters, and you'll take a key that is of the same size, so a 16-byte key, like a 16 bytes of letters, for example. We can split our plain text over what we call blocks, where every block has the same block size. And for every block, we basically apply our very super circular function with the block and the key itself. So we don't have to worry about what the function does, we just know that we have a function that does it, and it outputs a ciphertext block like CI. And then we kind of like concatenate all the blocks together. So if our plain text is like B1, B2, and B3, we independently obtain C1, C2, and C3, and we kind of like put them together side by side. And this is what we call a block cipher, because we are doing this over blocks, each of a certain size. So far, so good? Alright, and so this is where we start to introduce what we call the AES block cipher. So AES, or Advanced Encryption System, is itself a block cipher, and we're looking at what we call the ECB block cipher. So the AES ECB block cipher, the logic is very similar to block ciphers that we discussed already. We have our super secure function f called encrypt. Don't have to worry about what encrypt does for now, but it basically takes in a key, and it takes in a 16-byte long plaintext, and it outputs a 16-byte long ciphertext. So we split our plaintext into different blocks, each of size 16. We run the function, and we output the ciphertext, and we merge them together to form the combined ciphertext. So this is basically how block ciphers generally operate. We split our message into blocks, run them through the encrypt function, and get the output. Later on, I'll give a demonstration on how to use AES or Python, but for now, we'll start by exploring what ECB actually does. So I'll give a forewarning that the next few slides I will be skipping through because they are not very relevant to the workshop. But if you're interested in cryptography, feel free to reference the slides and try to understand what ECB is doing. But anyways, ASCCB has a 16-byte block. We'll have a block S where we'll use like B0, B1 to B15 in every byte in the block. We'll use a 16-byte key and we'll have 10 rounds. What rounds are, I'll cover later. But for now, we'll suppose our block, which is 16 characters long, we kind of like write them down into a 4x4 array or 4x4 matrix, kind of like a square like this. And then, from the key, we derive 10 different keys of 16 bytes long. And we use 4 different functions to play around with the block. Add round key, subbytes, shift rows, and mix columns. And essentially, this is what's happening every single round. So every round, from our 4x4 square of each square being a character, we store it with a round key, we substitute it using some substitution box, we shift rows, and we mix columns. High level overview, this is the only reason why the key is being used. This is being used to break linearity. I will not cover what linearity is. It is a very advanced concept, and I do invite you all to figure out what linearity means yourself.
Yes.
Anyways, shift rows is responsible for the diffusion, and mix columns is doing diffusion as well. Because in shift rows and mix columns, you are making sure that everything is going to be used by another thing as the rounds progress. So in 10 rounds, this one byte will be shifted like 10 times. It will affect 10 different portions. And mix columns ensure that each row is being mixed together in a column. So you can think of this as basically, it kind of just takes a key, takes a message, splits it into 16 items, and it kind of just throws it into a boiling pot, and it cooks it for a bit, and then it outputs something. That way, everything is infused into each other, so it's super hard to kind of like break it. And for those of you who want to do cryptography or who are interested in covering what each function does, you can reference the slides here that we'll be sharing at the end of the workshop. But if you put them together, you basically get something like this, where to encrypt a block, you convert the plaintext to a 4x4 matrix, you add the round key, and over 10 rounds, you kind of run sub, shift, mix, and add round key. Then you finish it up by doing a bunch of operations and finally converting it back to a 16-byte long string. And the decryption algorithm is basically the same thing, but you invert the order. So from the encryption algorithm, we kind of like reverse it and go upwards. So for decryption, we first convert this to a matrix. We then add the round key back. We invert shift rows, invert subbytes. So INV is basically a function that inverts, so it undoes something. So it undoes, and then across the remaining 10 rounds, we undo round key first. So we see how this is the last operation, therefore this is the first operation. Then this is the next operation, this is the second last operation, so our second operation is to reverse it. So we slowly reverse it one step at a time. And as we reverse it all the way to the end, we'll get back the plaintext. So this is how AES essentially operates. Don't worry about the details, because the details is kind of like, it is quite complex, and I would recommend being familiar with matrices first. Yeah. So, FAQs. Do I need to know what AES-CCB actually does? No. Because what we've done through is just a look into the inner mechanisms of one of the most commonly used encryptions in practice today. Diffusion and confusion are still relevant concepts in symmetric cryptography, and generally for a beginner CTF like BlahajCTF, you only need to know how the ciphers operate. So as long as you can visualize the encryption as just each block is being encrypted to another block, you'll be fine for most of training anyways. And for an FAQ on how to implement AES, I'll be doing a live demonstration. Alright, so from here, we just need to open Python, and then from crypto.cipher import AES. So if you want to initialize to encrypt something, we do cipher equals to AES.new. Oh, right, sure, I got you. Yes. So once you imported the AES library in crypto.cipher into the system, you can run AES.new. Don't press enter yet. Oh wait, we need a key. Hold on, I did that. So we first need a key. So to generate a key, we can do key equals to. Okay, someone give me like 5 characters. I have BlahajCTF, okay. Anything else? We need like 10 more characters here.
It's cool.
It's cool.
Does that work? I don't know. I randomly pressed. I randomly just said.
Okay, whoever said it's cool, you're responsible for shutting down this screen. Alright. 1, 2, 3, 4, 5, 6, 7, 8, 9. We need one more. We need one more. We need one more. Alright. Let's check the length of the key is 16. Okay, perfect. Now, we do cipher equals to AES dot new key AES dot mode underscore ECB. So what this does is that we initialize it with a key, BlahajCTF is cool, followed by AES dot mode ECB. The way of we are telling Python that we are going to use ECB, AES ECB. Alright. Now I'm going to get a message. Someone shout me like a sentence you want me to like encrypt or something. Okay. Let's say I want to do ABC, D, E, F, E, something like this. Just nice, we have 16 bytes in our message. So we do cipher dot encrypt message, and we do something like CP equals to this. So CP is our ciphertext. If your message is not a multiple of 16 in length, you will get an error. For example, cipher.encrypt, let's say I do like A. You'll get an error because your data must be a multiple of 16 in length. So encrypting like one character won't work, but if you encrypt like 16 characters in a row, you'll get an output. So when you press CP, after you encrypt, actually I should give us some time. Okay, let me know once you are able to successfully encrypt any message. So like my message is A, B, C, D all in T, and then my key is BlahajCTF is cool. So if you guys are following the same example, your ciphertext should look exactly the same as what I have over here. Alright.
So like, because usually messages have like variable length, right? Why is it more or less consistent?
I'll get to that later. Alright, so you may notice that the ciphertext is a bit like weird, right? Why is there so many like slash X's? You'll notice that if you count every character, your ciphertext is more than the message. But my message is only 16 characters. So why is this more than 16? The idea is that slash X is Python's way of representing a character. Slash X08 means the byte that is just 8. Caret is just a byte that is caret. Slash X88 is a byte that has a decimal equivalent of 8, which is in hexadecimal. So you'll see that like if I do 0x88, which is writing a number in hexadecimal, we get 168. And if you want to check the second character of ciphertext, the third character of ciphertext, we get 168. So this is a bit of an intro into representation, but generally this caret, the second character, which is 94, and slash 8 is the third character, which is 168, and you can see it's like exactly the same as that. So this is one character, one character, one character, one character, one character, one character. The R is a character, 7 is a character, FC is one character, T is one character. These are all individual characters, E and FF. So those are all individual characters in the way that Python will represent it. If I were to do list of CT, you will see that I get an array containing these values, and you will notice that each number corresponds to each byte inside. So C slash X08 means the byte that's a number 8, therefore our first element is 8. Then this caret on the SC table is 94, this is 168, O is 111, D0 is 208, K is 75, and you can kind of see the rest go on from there. Another way to represent bytes, aside from this, is ct.hex. This will output a hexadecimal string that contains the bytes themselves. So 08 is the same as 08 here, A8 is the same as A8 here, and every 2 characters is being used to represent one value in there. To convert this back, we can just do bytes, and this is important for training, by the way, because a lot of our data is stored like this. You can do bytes from hex, or bytes dot from hex, and this essentially is equal to our ciphertext from earlier. Alright, I'll pause for a bit, and if anyone needs questions regarding to the demo, feel free to sound out. Is anyone lost as of right now? Alright. So now we have the ciphertext. How do we decrypt it? Well, we just do AES. So recall earlier we have to decrypt a message, we basically just reinitialize our cipher. So we do cipher equals to AES.new key AES dot mode underscore ECB. And then we do cipher dot decrypt CP. And we see that it actually we get back our original message, which is A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Yep. So you may notice that I wrote the same line of code twice. Earlier, to encrypt something, I used cipher equals AES.new, and to decrypt, I use the same thing. It is, as of right now, using mode ECB, you can just use the same cipher. But the reason why I'm using this cipher twice is because when you play around with stuff like AES mode CDC or CPR, to decrypt, you must reinitialize the cipher object. But we'll cover that later. In the meantime, as another example, let's say I have a message that is like A times, let's say 16, plus some message like B times 16. Now, when I do cipher.encrypt M, you get one long hex string. But at the same time, to show that it's a block cipher, when I'm just encrypting the first 16 bytes of the message, you'll see that it's almost identical. Like all of this, the first 16 characters are the exact same as the output of A times 16. This is because it's a block cipher. It takes in every 16 bytes and it outputs the corresponding block. So here, my message has one block of all A's and one block of all B's. When I encrypt it with ECB, it outputs the encryption of all A's and encryption of all B's and puts them together. So you will notice that when I encrypt B times 16, I essentially get the last 16 bytes of my output of M. So I can actually derive cipher.encrypt M by just calling encrypt on every single 16 byte block one by one. And of course, if I want to decrypt something, I can just do cipher.decrypt, and then I'll just like put whatever stuff I want to put here, and then it will return with them. So in my example, I can just highlight this, and then I will push it back here, and you can see that when I decrypt it, I re-get my original string, all A's and all B's. And similarly, when I want to copy and paste the encryption output of all B's, so which is this, and I put it back here, we get all B's, because it's doing this one block at a time. So here, I have one block of all A's, one block of all B's, encrypt and decrypt will basically just only focus the operation on one block. So far so good? Okay, in the meantime, I'll be sending code on how to do encryption inside. Oh wait, no, there's more stuff. Alright, so As someone did ask just now, what if my size of my message isn't a multiple of 16? Because we know that when your message is like 1 or 2 or 3 bytes long, you will error, you need it to be a multiple of 16. This is where what we call padding comes in. So, because block ciphers require plaintext blocks to be a fixed size or a multiple of that size, because as AS is block size of 16, your plaintext is either 16 bytes, 32 bytes, 48 bytes, or multiples of 16. To ensure that the plaintext will fit the right size, we use what we call padding. So from PyCrypto, you can actually import what we call pad and unpad functions from crypto.util.padding. And if I have a message like 12345, which is not length 16, we can run pad message 16, and Python will just add a bunch of bytes to the end of message such that it is exactly length 16. So the padding algorithm that Python uses is what we call PKCS. I do not know what PKCS stands for, I just know that it's called PKCS. But generally speaking, if you have a message of size m and a pad length of size k, so here we're trying to pad it to 16 bytes, k is 16, and m is like 15, you will append however many bytes we need. So don't worry about what this value means, but generally speaking, if I need to pad things to be a multiple of 16 and I have 15 bytes, I only need to add 1 byte. If I have 14 bytes and I want to pad it to a multiple of 16, I just add 2 bytes. And the bytes that I added will contain the exact value of the bytes to the end of the message. So this is probably where it's a good idea to kind of like do a demo. So from crypto.util.padding, you can import the functions pad and unpad. 1 second. Yeah, that's all. There we go. From crypto.util.padding with a capital P, import pad and unpad. So if I have a message like say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you will see that the length of the message is 10. It's not a multiple of 16, we need 6 more bytes to pad. When we call pad m and we specify 16, so we let it be like pm equals pad m 16. pm itself has the same message string, but it adds a bunch of 6s to the end. Anyone knows why the padding byte is called 6? So the reason why the padding byte is all 6s is because when you calculate, you need 6 more padding bytes. So I'll pad it with all 6s. That's more or less the general reason why. So if I want to pad something that's like say a okay, wait, I should probably do this with a message. So let's say I have another message. We'll call it A, and it's like it's A times, let's say 11. Now, when I do pad A and I pad say 16 bytes. Okay, quick question. How many padding bytes do I need to add to A to make it a multiple of 16? 5, right? Correct. So you will see that it adds 5 bytes. On the other hand, if I want to pad, let's say like, okay, I'll just use like A times, let's say 13, for example, we need 3 more bytes to complete it to make it a multiple of 16. So the library will basically just add 3 bytes, and each byte itself that it adds will contain the number 3. There's a reason behind this, and I'll cover this later. But in the meantime, if let's say I have, say like length 28, for example, in order for 28 to be a multiple of 16, we actually need to add 4 bytes. Because 28 plus 4 is 32. So we'll add 4 0 4s to it. Alright, and of course, this makes very little sense. But if a message is already a multiple of 16, it will add 16 16s to the end of it.
You just go to the next multiple.
Yes, it will go to the next multiple. So you may notice that it says 10, right? Like 10, but 10 in hexadecimal is 16. So if I convert this to a list of pad BA something 16, look at this. You will see that it is 97s followed by about 16 16s. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, there's like 16 16s added to the end. And this is to make it a multiple of 16 no matter what. Now, if I want to unpad something, so like remember our padded message 1 2 3 4 5 7 9 0 6 6 6 6 6. To unpad it, we just call unpad PM, and then we put in the same number which is the size that I'm padding it from. Then you'll remove the padding bytes and we get back our original string. So for example, if I do like pad A equals to pad, let's say a string of A times 11, and then I do unpad of pad A, I need to go with block size 16. You will see that we get back our original A string, which is just 11A, and you'll notice that all the padding bytes in pad A are gone. So for reference, pad A, right? Can someone tell me what the last byte of pad A will be? Or the number that corresponds to the last byte of pad A in this example? Right, think about it. So pad A, right, is pad of 11 A's, and padding to a multiple of 16, right? Yes, so I need 5 bytes to pad with. So the last byte of pad A is 5, because I need to pad by 5 bytes, so I add 5, 5, 5, 5, 5. That's basically how padding works. And so when I call unpad, what unpad is doing is that unpad takes in the last byte of the message and it removes that many bytes from it. So, because the last byte of pad A is the number 5, the unpad algorithm will take that value 5 and it will go, okay, I'll remove this, I'll remove all the 5 bytes from the message, and it will make sure that the bytes that I'm removing is equal to the size of the padding. Because if I start removing more stuff like the A's, I will realize that I'm removing parts of the message that shouldn't be removed. I should only be removing the padding. Therefore, it will error. So, for example, if I want to say unpad a message that is like A times, let's say like 15, and then I add a byte of like a 1 byte here, you'll see that I get 15 A's. And this is because unpad takes the last byte, which is a 1, and removes exactly 1 byte. And similarly, if I put in a byte that's like 2, you will see that it has an error, that the padding is incorrect. This is because unpad goes to the last byte, which is 2, and it goes, okay, so I need to remove 2 bytes. But as I'm removing the first byte, which is 2, the previous byte is A, which is not 2. So something is wrong, and therefore it triggers an error. On the other hand, if my message is say like 14 A's, and I put in 2 2's, so like this, you will see that it runs just fine. It removes the 2 bytes of 2, and it gets 14 A's back. Alright, I understand that here it may be a bit confusing. So if anyone has any questions, do like raise your hand or sound out, and I think the trainers can come over and help you guys. Yeah. Right. Anyone needs any help with understanding this so far? Okay. So the reason why I'm like covering padding in general is because there is a certain attack on AES called padding oracle. I will not cover it, but as far as you're aware, will it be the CTF? Yes, it will be in the competition. But I won't be covering it because it is a kind of intermediate concept, so I won't be covering it in this workshop, but I do invite you to explore the idea of padding oracle. The idea is that we are using the concept of padding to slowly recover an encrypted plaintext by being able to query a decryption oracle multiple times. Alright. So, as I mentioned, unpad takes the last byte of the message, reads it as a number, and removes that many bytes from the message. So, for example, in here, I have 3's 13 times with 3, 3, 3. So when I unpaired it with respect to the size of 16, it takes the last byte, which is a 3 in memory, and removes these 3 bytes. But if I unpair with 3 again, but I don't have the last 3 bytes being the same, then there will be a padding error, and it will say that, oh, value error padding is incorrect. So for those of you who are wondering why, when I pair a message of size 16, the reason why it adds 16 more bytes to it is so that unpaired will just remove the extra block, and it wouldn't raise a padding issue. All right, so we'll pause this lecture as we are halfway there for a break. So this is for you all to go for a toilet break or to ask questions or to approach any of the trainers regarding the content so far. Yeah.
Sorry.
Yes.
But if you have a 16 byte long message, right?
Yeah.
But then you had it, so it'll be 32 bytes long.
Alright.
So the key, if the rest of the message is using a 16 byte, is it still able to encrypt the 32 byte?
We can try this out, or we can experiment this out. So let's say I have cipher equal to AS or new key AS or CD, right? And my message is like, let's say of 16. I paired message with 516. You will get 16 more #10. When I do cipher, when I do cipher or encrypt EM, which we'll call, let's say, TPM. TPM will have a length of 32 because we are sending in 32 bytes to it. And if I open TPM, you'll see that the 16 bytes is the encrypted message, and the remaining 16 bytes is the pending encrypted AES. So if AES will encrypt the entire message including the pending, then usually how people would decrypt it when they're called decrypt on the function. But decrypt will only reverse the effect of the encryption. So you still get OE, but you get 16 zeros. And then they will call unpaired. So unpaired or cipher decrypt. So you just write down unpaired. And then that returns ESP.
So it's still
Yes, it's still encrypted padding. This is actually very important to padding oracle, where the attack uses the knowledge of the padding to figure out what the original data is. Yeah. I will not explain it for now because it can be very confusing. I do recommend putting out a video or looking it up online. It's a very interesting concept. Yeah. I'll go through the yeah. So yeah. Oh my god, this is...
turn it up.
Okay, so now that break is more or less over, I understand you guys will be tired, but we are almost done. We are more or less halfway through the argument part already. So, I'll end off the part of block ciphers by talking about other block ciphers. So there's like ASCBC, Feistel, XXT, Blowfish, etc. You feel free to look those up on your own time. But one of the things I feel led to cover is ASCBC, which offers what we call more diffusion. So as a recap, ASCB is a block cipher that takes in every 16 bytes and encrypts it into an output ciphertext. So ASCBC is supposed to kind of do something similar, except now, because every block only contributes to one block, now the previous ciphertext block is being used as a XOR to the next plaintext block into the encryption. So it's a bit complicated, but the whole point is that I'm involving the previous block inside the next block, and there's a reason for this. So ASCBC uses an IV, which is called a nonce. This is a 16-byte string, and if we have blocks P1, P2 to Pn, each of size 16 bytes, and encryption, be the ASCB encrypt function, then we can write it as C1 is encrypt P1 is XOR with IV. So XOR is the XOR operation, and IV is some 16-byte initial string that is being XORed with the first plaintext. And then C2 is plaintext 2, XORed with C1 and encrypted. And then, of course, like the block Cn is the encryption output of Pn XORed with Cn minus 1. Any questions with this so far? Alright, so this allows for a diffusion of previous blocks to diffuse into the next block as it's encrypting. Because the output of C2 not just relies on the plaintext 2, but it relies on plaintext 1. Because plaintext 1 affects ciphertext 1, which affects ciphertext 2.
So you change one in the plaintext block 1, everything down the line will change.
Correct. The moment you change anything in the first plaintext block, everything else output will be different. So there's like more diffusion. And the reason why we use ASCBC and not ECB is because there's a certain issue that goes by the name of an ECB penguin. You can actually Google this, by the way. But the issue that is called ECB penguin is a problem that's prevalent in ASCB, and ASCBC is there to kind of like prevent it from being an issue. Actually, we do have time to kind of like go through it. So I don't know if you can see this penguin, but this penguin is a result of using ASCB to encrypt the image. Because every pixel is more or less the same color, we encrypt a 16-byte block that is the same, the output will be the same. So because of that, all the white colors of the originally white picture is now this color, all the black is that color, and in the sense that the image is still there, you can still tell it's a penguin, but you want it to actually encrypt into something that's intelligible. That is the ECB penguin issue. So one thing that ASCBC does is that there is a very interesting attack that we call spoofing with a user-controlled ID. So I will give a case scenario, and then I'll invite you all to try and figure out how to break it. Suppose we have an authenticated system that takes in a user ciphertext packet and it decrypts it into a JSON or like some data. So for example, it decrypts a user input ciphertext and it gets something like admin false. So this is basically telling the server that, oh, this user is not an admin. Let's say we have a flaw whereby the system allows users to also pull in the IV field. So the user can put in their own encrypted data, which is an encrypted output of admin false, and they can also put in their own IV. Can we break it? Can we get a valid ciphertext that will decrypt into admin true, so that when we log on to the system gives us admin rights and we can wreak havoc on the system? So this is where the cybersecurity part kind of like comes in. So let's do a recap. We know that the ciphertext is encryption of admin false XOR with ID. And similarly, the decryption or CBC decryption will be admin false XOR with ID. Does this make sense so far? Alright, so does anyone know, or anyone happens to know, how we can change our ciphertext or our IV into something that when we decrypt and XOR it back with the IV, we get something like admin true?
We have knowledge on IP.
Huh? Sorry?
Below IB.
Yes, you know ID.
You know how to? I don't know.
But we can control what ID we put in and what ciphertext we send to the server. The server just decrypts the ciphertext with the ID using a key that we don't know, and then resolves it back with the ID to get the data. Right, what IV Zor decryptability is an false.
Yeah, but the server's doing the operation.
Yes. We can control the IV and the CT
Okay,
pins.
wait, but you can't sign.
You have a right idea, but you're almost there actually. So, you want me to show the solution now, or you want to actually spend more time thinking about it?
It doesn't work with sound decrypt CP with IB.
You cannot, because you don't have decrypt CT.
Oh.
You only have CT and the IV. Because the encryption is done by the server with a key, and we know that AES is secure, so we can't break it to find the key. So what we want is we want a payload that when we decrypt it, we get admin true. And remember the fact that we control IBs and ciphertext. So we want to find a certain IP, which we call IB prime, whereby IB prime XOR with admin true is the same as admin false XOR with the IB. Then we can actually send this new IB and ciphertext to the server. Note, because we already have the IB and admin false, and we know admin true, these are just strings that we can write out, we can XOR it back to recover IB prime. So now, when we send the packet IB prime and CT to the server will do decryption CT XOR with the IB, right? So this will become decrypt CT XOR with IB prime, which, as we said, is going to be IB prime XOR with admin true XOR with IB prime, and this gives it admin true. So this actually lets us, essentially, so if we have a system that uses ASCBC, and it gives us the ability to control our own ID and ciphertext, we can modify the ID in a way such that we can change the decrypted payload to be anything we want. So for now, if anyone's confused, do raise your hand and we are open to for you all to ask questions before we move on. So in CBC, IV is a initial vector, or we call it a nonce. So in ASCBC, you have an IV that you XOR with the plain text and you encrypt it to get ciphertext. So when you encrypt a message or when you encrypt a plain text, the server will normally generate a random IV and it will send you the ciphertext plus the IV string. So when you receive the data, you will have not just ciphertext but the IV. No, IV is known. IV itself is known, and by default, most systems they won't have this vulnerability. They will at least do some checks, or they will try and involve a different way for you to prove that you have admin rights. And if anything, they will not do something like admin force into a cookie or into a data that you control. So this is very helpful in when you solve a web challenge. So there can be a web challenge as an authenticated server that accepts an IV and a ciphertext, and the ciphertext decrypts to some string. They may give you permissions that you are not supposed to have. Any other questions? All right. Then we finish our block ciphers and we move on to stream ciphers. We are more or less 75% done with the content, by the way. So, block ciphers, they require what we call fixed sizes or fixed size. And otherwise, if the message isn't a fixed size, padding is used. So one of the questions would be, is there another way? And this is where stream ciphers come in. So if you have a message M of a certain size, you can consider a function that takes in a key and a size, and it generates some random string of bytes of length size. This stream, we will call it a key stream. Then our encryption method is just ciphertext equals to the key stream XOR with the message. So FKSE is, okay, I just realized that FK kind of sounds like a vulgar word. That was unintentional. But FKSE basically generates a almost random stream of length size, and it is XOR with the message stream to recover the ciphertext. This is what we call a stream cipher. That way, our message can be of any length, and we don't need to use any padding. The only thing that varies is the size of the key. So we also should note that our function doesn't just need to take in the key and the size, it can take in additional values like a nonce. So as a diagram, right, you can think of it as this. I have a plain text here, and my stream cipher will take in a key and some ID, for example, and it put it through a key generator function that generates a bunch of like ones and zeros called a key stream. Then I saw this with the plain text to get a ciphertext. And to decrypt, I just run the same key and ID through the same key generator to get the same key stream, and I saw it back to get plain text. Remember how I said A or B is A, right? This is the same logic that's being applied here. And for security, because every ciphertext is a message absorbed with a key stream, the security lies with the key generator function, in that it must be able to generate a stream of almost random bytes given an input key.
And therefore RNG.
Yes, there's some level of pseudo-randomness being used here. But we cannot use the same key to encrypt two different messages. Does anyone know why? So if I have C1 equals to P1 XOR with the key stream f of k, and I have C2 which is P2 XOR with f of k, and if I know P1, P2, C1, and C2, right, I can derive C1 XOR with C2 to be P1 XOR with P2, because the key stream is XOR back with itself. So if I have P2 and C2, and I want to know what the decryption of C1 is, I can just use XOR, and I can recover P1 as C1 XOR C2 XOR P2. Yeah. So you notice this is where all the XOR that I was going about comes into play, because it's being used to understand this. So if we know one plain text ciphertext pair, we can decrypt any encrypted message without knowing the key itself, because it will be sorted away. So far so good? So in here, right, the stream cipher is doing ciphertext is plain text one XOR with a function that takes in the key, right? And similarly, if we know another like ciphertext and another plain text, we know that, so let's say like we have C1, C2, P1, P2. So we encrypt two messages. One message we don't know what it is, but we have the ciphertext. The other one is we know our message and we encrypt it to a server to get a ciphertext. So we have C2, P2, and C1. We want to know what P1 is, which we are. So we aren't allowed to get P1, but we want to know what P1 is. The idea now is that from C1 and C2, which are like equations written in XOR, if we XOR C1 and C2, is P1 XOR Fk XOR P2 XOR Fk. And the Fk cancels out to P1 XOR P2. So if you want to know what P1 is, we just do C1 XOR C2 XOR P2 to get P1. So in a sense that yeah, so for stream ciphers, you cannot use the same key to encrypt a different message. If you're encrypting any message, you must always regenerate a key, which is why we use an ID or a nonce. That way, we can keep one static key, but we generate a random ID every time we want to encrypt something new. That way, as long as we don't repeat the same nonce and the same key, the key stream will be unique to every message and can only be recovered if I know K. So that way, the security of the cipher is no longer the fact that key and ID may be reused, because I randomly generate the ID every time I encrypt something new. So it's very unlikely, more or less impossible, that ID and key will be the same. So now the security is basically how secure is the function F. And this is where we introduce another mode of AES that is also useful, called AES-CTR, or AES counter mode. AES-CTR is an algorithm whereby we split the plain text into blocks. So it's still like a block cipher, but it's also like a stream cipher. But the general idea is that for the ith block, so like for block P1, we use the key, we perform AES-key encryption of a counter plus I. So counter itself is basically a nonce or an ID nonce that slowly increments from 0 to 1 to 2 to 3 depending on each block. We encrypt that instead of a message, but we use that as a key stream that we then XOR with the plain text to get C1. So here, C1 is P1 XOR with encrypt K and counter. C2 is P2 XOR with encrypt K and counter plus 1. So this is pretty much secure as long as your ID, which is your counter, and your key pair is not reused. If it is reused, then you can use the same attack that I mentioned earlier over here to recover the original, to recover any message that shouldn't be recovered. Because if the inputs to the function are the same, we can use the XOR method from earlier to get it back. Alright. So with that in mind, I feel like it's probably relative that I do a demo on ASCBC and ASCDR. So if you go back to your computers, remember that we have our crypto.cipher import AES. I'm going to show you guys how to basically generate a random nonce, a random key, and use it to do CBC and CTR encryption. So we're going to import this library called OS. So OS is a systems library that Python uses for many stuff. One of the functions that we use is urandom. Urandom has a property whereby if you enter, like say 16 bytes, it will always generate 16 random bytes. I'll leave this here for like a few quick seconds for you all to like write this down.
Oh, yeah, I can.
Alright. So now that we have urandom, now that we've imported our functions, we can do something like ID equals the urandom 16. So this is a random ID. This will generate a random nonce. And we can also have our key be urandom 16. And you will notice that the key is not equal to the ID. They are different things. The key itself and the ID are different. So let's say now I have a message. Message equals to a change I didn't decide. Hello. So if I say, okay, let's say for reference my message is not like 16. I will just do add message 16 to add it. And then I will do, okay, so before we even do anything, we need to initialize our cipher. So we do cipher equals to as.new. So if you are doing AS mode CBC, we need to specify an ID or a nonce. So we'll do AS mode CBC and ID, like this. Because CBC requires an ID and a key, we put it like so. We put it like so, and then now, if PS is at message 16, we can do cipher.encrypt as a message, and we put it as CBC ciphertext. You can see that CBC is the output of it being encrypted. I'll give you guys about like 2 to 3 minutes to kind of like follow along. You will notice that your output will be different because your key and your ID are completely random. What your key and ID is will be different from what key and ID I generate. But now, to decrypt it, you will notice that we cannot use cipher.decrypt because it's CBC mode. So we have to reinitialize a new cipher. So we run the same code again, cipher equals as new key, CBC ID, and then we run cipher.decrypt, CBCCT, to re-get our original message. The reason why we cannot decrypt after encrypt is because CBC relies on the previous block. So when we decrypt it, we need to get it to reset the use of original ID instead. So when we call cipher.decrypt CBCCT, we must reinitialize a new cipher, which is the same key and ID parameters, to undo the encryption. So far has everyone been able to recover the original message? Alright. If anyone has any questions so far, do like sound down and raise your hand, and the couple trainers will come over to assist you all. Yeah. Yes. And Azazel, Junheng. Oh, never mind. Okay, I'll come to you first. I'll come to you later. Alright, for the pad and unpad functions, right, do like 3, 4 pad, so you do pad it. because run twice. Okay, never mind. Alright. Oh. So another interesting fact is that if I call cipher.decrypt on the same thing again, I will get a different output because CVC works by taking the previous block inside. So if I call cipher.decrypt this and I call it again, this same cipher will be decrypting it as if it is decrypting key repeated twice. So the output will be different. Like for example, if I do this, I do cipher.decrypt CVC plus CVC you'll see that you get the same output as hello101 followed by this random chunk that happens after. Because when I call cipher.decrypt twice, I'm calling decrypt on the same cipher. So it's the same as I'm just taking the both of these blocks and running it again. Therefore, there's a need to reinitialize the cipher object when I'm already trying to decrypt something. Anyone needs help with following the demo for now? Just raise your hands and then we can come and assist you all. Yeah. Alright. In the meantime, if you want to encrypt using AES mode CPR, we can do cipher equals to AES.new key AES.mode_CPR and we must do nonce equals to ID. But you will see that there's an issue and that the nonce is too long. This is because in ASCPR, your counter or your ID nonce is up to 12 bytes long. So we will have to do something like nonce equals to u random 12. This gets a random 12 byte string, and then we can do nonce equals to nonce here, and it will work fine. Then to encrypt our message, we can just do this, and then I believe we cannot run cipher.decrypt again. Instead, we have to reinitialize the cipher object and then run cipher.decrypt in the ciphertext. Like this. This gets us our original message back. And you will notice here that we don't need to pair our message because ASCPR is a stream cipher, so we don't have to pair our message to a multiple of 16 for ASCPR. This is more or less the end of the demo. So if anyone needs more time to look at the screen to write it down, do like raise your hand. Yeah.
I don't really get all the CPR, like how the stream is like, because you really have the key and then you have the key, like, which is yeah. Then you specify nonce, which is like,
No, I think for CPR, so the stop in the CPR, but generally, so the idea is that no one can. Okay, so I didn't cover even cover this by side to cover it because but there's a desktop padding corridor, whereby if you are doing your padding correctly, you can actually give the cycle the movement any arbitrary cycle set or encrypt any arbitrary set using the padding corridor. So because of that, you can stream cycles instead, which either split. That way there's no need to use padding. Yeah.
but you say stream cycle generates a key.
Yeah. A key stream. Yeah. From the key that you yes. Oh. So the key stream itself is if you find that it's in the key itself in types, right? Then brings up some so the key stream is some random generated box, but it doesn't necessarily it should be possible to the key stream itself is the same.
And the key can be anything. So the one
Okay, in ESCR, the key has been language
oh, so it's a constant.
for CPR. But for things like, say, like RC4, the key can be any language.
What about ID?
Oh,
ID you generate now, which is less than 12
okay, in CPC, ID must be like 16. In CPR, ID has to be like less than 12. Less than 12. because of the counter, right? So integral is like counter 0, 0, 0, 0. Next one counter 0, 0, 0, 1, 0, 0, 2, and calculate from there. So that is the part that you can, but the counter has to be less than it cannot be more than 1. Correct. Then the north is just 1. Then I'll buy it. So the equation measurement is Alright, I will be sending sample code to encrypt using ASCTR and ASCBC later on in the training announcement. In the meantime, we'll move on and we will cover, so in general, encryption is ciphertext equals to M message XOR with a function taking the key and ID. Decryption is the same thing, ciphertext is XOR with a function with the key and ID. Oh, actually, you guys see it.
Because it's different from the key stream. Key is not key stream. It's like you put in the key, right? Then the machine is the encrypted. Then these are key streams. Yeah, then this key stream, you use it to store ID.
I'll move on to the lecture for now. We are almost to the end of the lecture, so do stick around for a bit longer. We are almost done. After which we'll be releasing training challenges for you all to play around with. So in the meantime, to explore, there are other stream ciphers that you all can reference, such as RC4, Cha-Cha-20, one-time password, or just using Python's random library to generate a secret random sequence. Yes. And so on and so forth. You guys can also feel free to Google these on your own. Yep. And one thing about ASCTR that we'll be exploring is what we call CTR malleability. So this is a different context where Alice sends a message to Bob using ASCTR. Let's say a malicious attacker like E drops the message and takes the encrypted message to C. I will tell you that if it's in ASCTR, E can maliciously modify C such that when Bob decrypts it, it becomes a entirely different message that E can choose. Our question is how? So the context here is that I have a message M that's encrypted into a ciphertext. Anyone can take the ciphertext and replace it with a different one that when decrypted with the same key becomes a different message that you control. So you'll be using the idea that encryption and decryption is just storing with M, K, and ID. Alright? And does anyone know how to replace C with something that, does anyone know how to set a different value of a ciphertext that when decrypted returns a different message that we want them to see? No, we don't control the ID.
No, you only get J to C.
Yes, we can only choose. Yeah. So let's say we have a message M, and we want the decryption to return a different message called M prime. And we are only at C. How can we generate some C prime that we decrypt it returns M prime? You can actually do this by writing down the equations, the solid equations on pen and paper and figuring it out. F is the ASCTR F is basically the key stream that generates C. F is the function. Yeah, F is the ASCTR. but you don't know the key and ID usage. So you cannot yourself. You only have the ciphertext key. So I have C and M, right? So Alice sends M to someone, and I take the ciphertext C. I want to replace C with some C prime. That when the person decrypts, they decrypt a incorrect value M prime, and I want to control the M prime. So given an M prime, what C prime can I send over that will decrypt that value?
M value.
Huh?
M value.
No value.
So I have this message, so I have this message, I have this message, so this is the stuff.
You only know C and M, and you want to like change. You only have C and M, and you're trying to change it such that for any M prime, you have a C prime that will. Yes. Yes, correct. So the idea is that you send C prime equals to C dot M prime dot M. And the reason behind it is that when I do decryption, it will do decryption of C prime XOR with the stream cipher key stream F, K, and IB,
Is M prime?
which is C dot M prime dot M XOR function. And we can further simplify C to M XOR F, K, and IB, right? So we have this. And then you will notice that you can rearrange the terms in the XOR operation such that they all cancel out except for M prime. So this is how, from ASCTR, we can change any ciphertext to decrypt into a message that we want, provided we know the original message. Yeah. Any questions so far regarding how this works?
Just transform.
Alright, and with that, oh right, and here right, you can see that in ASCTR, integrity is not preserved because I can modify the message and the person receiving it won't know that it's modified. But with that, we come to the end of the workshop, so it's time for training, guys. So, Azazel and myself and the last team have compiled a bunch of training challenges for you guys to do as part of the workshop. I believe Azazel will send the distribution shortly in the Discord. You all can unzip it and play around the challenges. So there will be RSA challenges as well as AES challenges for you all to do. I will let you know that some of the attacks may have already been covered in the workshop. I'll try and send the slides shortly after this. And yeah, so that is the end of the training session. Yeah. Okay, everyone, we'll be going through some of the challenges in 12 minutes time. So this is just an FYI, in about 12 minutes, Azizu and myself will be going through challenges that you all want us to go through. And then we'll do this until like maybe around 5-ish, and then that will be the end of the day.
Okay. Hello, test. Okay, hello everyone. We're gonna go through some challenges now. So,
No, the mic is like very hard. It works something like that.
okay, we're gonna go through some challenges now. So that's you guys should know we have 6 challenges. How do I do this? So just
I think they can just pick one.
yeah. So we have 6 challenges. Do all? We don't have enough time for all. I think. Can you guys just shout like which challenge you want to be shown? Walk through the most.
Keygen,
Okay, I share Keygen. Any more responses? Guess not.
No one going to go through the one
It's your
you're
challenge.
No, why is that true?
What? It has your name in the challenge? Yeah. That's your name in there. Wait, I said one of them has your name. Okay, you want to do it? I haven't looked at it at all.
Oh, what the more you should.
What? Okay.
Okay.
Okay, Maury is forcing me to do this because I've not looked at this challenge at all, so I'm going to be doing it live, I guess.
Yeah. Okay.
Thanks. Yeah.
You only got one part, you don't have two. Then I don't know how to do the next.
You should explain like
I'll explain about this
I'm
after I
doing
go
the
present.
different thing. The reduce. Solution means what? Like how to do. It's like the reverse. Like you need to find the statistic thingy, right? Then you need to no, statistic. The P and then it's P minus 1 plus Q minus 1. Then you only got one prime, you just use P minus 1. So your statistic, yeah, so your sign is yeah, and minus 1. Then you just continue like the normal way also.
Okay.
But I don't know why.
So I solved it! Yay! So I'll just briefly explain my thought process. So if you look at the source code, right, we have two main things that we want to care about. Firstly is this function that says API check key. We want to care about this because it's the thing that gives us the flag, right? So let's see how we can get the flag. So first, we give it a key. It's separated into the ID and the ciphertext. The ID is the first 16 bytes, and the ciphertext is everything else. And then it takes in that ID and it takes that ID and its own secret key, which is in this file that we don't have access to, and it creates an AES cipher instance from it. And then it tries to decrypt our ciphertext and checks whether it's equal to guest, admin, or something else, right? So we want our ciphertext here to decrypt to admin to get the flag and solve the challenge. The second route that we're interested in is this generate key thing. You can see that first it creates another AES CBC with our secret key up here. And then it encrypts the word guest, and it also gives us the ID. So the ID is at the front, the encrypted part is at the back, right? This thing is useless. It's just a check register response, I guess. So you don't really need to read the HTML source code. You can kind of guess. Generate key, right? So if we generate this key, we know that the first part, the first 16 bytes should be the ID of the cipher that's used. And everything else should just be the encrypted ciphertext for guest, right? And indeed, if you put our trial product key in here, it says valid trial product key because our ciphertext, our plain text is guest, right? So this is expected. Now, if you recall the structure of CBC from this slide, you can see that, okay, I'll just swap, wait, is there the, you can see that here, first the ID is XORed with the plain text, right? And then it's being fed into the encrypt function, which means that when we decrypt, we first decrypt it and then we XOR it with the ID for the first chunk, yes? So notice that in the, in here, we have a user supplied ID and also user supplied ciphertext. So for our guest ciphertext, what happens is that the cipher, okay, it'll be so much better if I could write again. That's fine. I'll see if I can write it. Okay. So let's just use E to represent the encrypt function, right? So we have that the trial key that we got from here, right? This is it's gone. This is the encrypted ciphertext of our guest string. Oh my god. No, if I use whiteboard, people in the stream can't see it, so. You can probably see it? Okay, that's great.
The screen, yeah, okay.
I'm just going to use this part down. Okay, yeah. So we know from our structure, it looks something like this, right? This is our encryption function. And we have our message, XOR with our ID. And out comes your ciphertext. So right now, what the trial product key is doing is that it's giving us the encryption of our ID XOR with the string guess, well, it's pattern, but yeah. So we want to be, well, we have this, right? And we want to construct the ciphertext such that when decrypted, it gives the string admin instead. So if you think about it, when this is decrypted, right, it first undoes the encryption function, and then it XORs with the ID. But you know that the ID is also, we supply the ID, right? So what if we change it to something else? Let's say say instead of giving the proper ID, we modify the ID. So we create a new ID, right? ID prime, such that it's equal to ID XOR the string guess and XOR the string admin. So now what happens if we give the server the same ciphertext as this, but with the ID as this? Well, the server's going to try decrypting this, right? When it tries to decrypt this, first it undoes the encryption, okay? And now it's going to XOR the ID that we supplied with this. So if you XOR these two things together, you get ID XOR guess, XOR ID, XOR guess, XOR admin, which you know that XOR cancels out, you do it twice, right? So you're left with admin. So wow, now you have turned guess into admin. I think yeah, it's basically this slide, right?
Yeah, look at that. Evidently, it's like we have no clue what's going on with this.
You have no clue what's going on.
With all, I just saw words and
So like the idea that you have the ciphertext and the ID, right? It's like when
for decryption.
the idea that like
You usually have this thing, but it's like it's based on the concept of challenge, and you have the ID and the ciphertext. So the idea is to use the same idea of ID prime to solve with your own design of output with what you have already. Then that will let you. So by setting this ID prime and using the same ciphertext, you will decrypt to the.
I said we know the concept, but the thing is that we don't know how to apply it.
oh, you don't know how to do it.
Okay. That's right.
Yeah. Plus, I didn't get how to like XOR with.
Okay,
Yeah.
so what I did was
I think this was something that as well. Something use focus also.
yeah, okay, so I think all of you guys should have Photos installed, right? I think it was Does that have that?
Yeah. Yes. Then import. Straight. No, this is the same extra. And then extra
Okay. So now we want to do a thing, right? We know that the front of this is going to be our ID, specifically the first 16 bytes. So what we can do is, so this is our XOR function. We want to replace the first 5 bytes of the ID, which is the first 5 bytes of this product key, with the ID prime, right? So we want to XOR the first 5 bytes of this with guess and then with admin, and then replace the first 5 bytes of this with that instead. So what we can do is, okay, let's see. So again, we have a hex string and we want to turn it to bytes, so we can use this byte.hex function. And then we know it's only the first 16 bytes. Okay. And now we want to change the first 5 characters of this ID, right? So we can do string XOR, and then we XOR it with guess first. Oh. All right, I'm so scared. Yeah, okay, yes. So this is the first 5 characters of our ID XOR with yes. Yes? I hope you guys can see this. And now we want to take this and XOR it with admin. Okay? And now we have this, right? So this is what we're going to replace the first 5 characters of the original ID with. So we want to turn it into hexadecimal first, and then we copy it, and we replace we can just count. That's 1, 2, 3, 4, 5. Yeah.
I didn't see that. Was that the Linux? I did awesome.
So in case people don't know what underscore is, it's the result of the previous expression. So basically, the underscore here is referring to this byte string. The underscore here is referring to this byte string. It's very useful. Yes.
Can I see the top?
Top?
Yeah, I don't know.
So just to recap, what we're doing is we first import a function that allows us to XOR together two byte strings. And then we find the ID from the original token that they gave us. We isolate the first 5 characters of the ID. And we know that we have to XOR it by guess and admin, right? So we get the first 5 characters of the ID. We XOR it with guess first to get this string. Then we XOR it with admin to get this string. And finally, we get its hexadecimal value. And now we want to replace the first 5 characters of our original ID with these. So we can go to this website, go back to this website, and just manually delete the first 10 characters and replace it with this. Does everybody understand? Is anyone who's lost?
I think I problem with Python.
Probably in Python.
Yeah. I can't even do a string. I did the encoding must be string or bytes.
No, sorry, it's string XOR. You have to import. You imported it.
Yeah.
So you use string XOR, not string. That was the typing.
Yeah. Oh yeah, that's why I was thinking. Sorry.
Yeah. In the meantime, does anyone else wants to go through another challenge, or you all want to move on this one? Yes. Sorry. Alright, so another challenge that we had, which required access to the server, was integrity. So in integrity, we have, so this is basically the code that the server is running. We have a message that is encrypted using ASPR, and this is sent to us. We are told to send the message over to Alice. We can send the same message over, and it will decrypt. And this is encrypted using ASPR, and it checks and it tells you what the plain text is. And the flag is only given to us if give me flag is inside the plain text, meaning that the plain text must contain give me flag. So, as an example, we can encap to the server, and it will show something like, after a while it should. Yeah, it says, please send this message over to Alice. This is a hex string, it's a hexadecimal representation of the byte string that is ciphertext, because you see it is encrypted, and then .hex is called to convert into a hex string. From the hex string, it will basically reconvert it back to bytes, and it passes it directly over to the function. So, if we send this same exact string inside, we see that the plain text is hello world, and then because there is no flag, there's no give me flag, like this is not inside the plain text, so it won't give us a flag. In order to give us a flag, we need to find a ciphertext whereby the digital output will contain this flag. And you may notice that this is very similar to our last slide on ASPR, in that it is malleable. So we just need to send a ciphertext that is ciphertext XOR with the difference in our messages as being XOR. Therefore, if we have, so let's say we encode again, and then we know that the original message is hello world,
Then we have our message that we wanted to send is give me flag. So we can do message prime equals to pad this 16. So this is message and this message prime message. We can basically do, okay, I'll use refill dot refill dot string dot. So we'll do mask equals to string dot message and message prime and message. Then from our server, we have hypertext is copy this, hypertext equals to bytes for text this. Then we do output equals to strings of hypertext with the mask. Then we get output, which is a bunch of bytes. But we know for certain from the presentation that this output, when we send this back into the server, it decrypts into give me flag, and then we get the flag here. So the idea, the premise is that we basically use what we covered here in C# availability, where we have cybertext and M. Our M prime is give me flag, our M is hello world, C is given to us by the server. So we just compute our C prime and we send it in to get the flag. Because it will decrypt into M prime, which is give me flag. Like a string sort is basically just does a source across the two byte string process. Yeah. If anyone needs help with understanding how we solve integrity through like that, anything else? Alright, I'll give it to you in a second. Then you can come over here. Alright. Any other challenge you guys want us to go through? Any like RC challenge or DPWA challenge or any of that sort? Oh, you wanted to do yeah. But you can pick one to go through that.
Okay, we're gonna go through one last challenge, which is this one, called RSA. So it's a pretty relatively simple setup, right? It's like a normal RSA setup. You generate your primes, you generate an inner message, inner ciphertext, but you have this extra value called hint here, right? And this hint is equal to 1337, 1337 times p plus 1337 times q, right? And if you look in this challenge or YAML, right, you actually see, oh, there's another hint here. It says p is equal to n divided by q. That's great. So if you would remember, okay, so there's actually a lot of ways to leak information about primes when doing RSA algorithms, and this is one of them. So let's see how we can kind of turn this hint value into an equation that might be useful to us. So from the hint, we know that q equals to n divided by p, right? So let's do this substitution where we get rid of q in this expression and we replace it entirely with p. So we have hint is equal to 1337 p plus 1337q, which is equal to 1337 p plus 137 n divided by p, right? And now, of course, we don't know what p is, but we do know what n is. We can do this thing now where we multiply by p on both sides. P squared plus 157. Okay. So now, if you remember, we don't know what p is, but we know what n and what hint is, right? So we have a variable squared. Is equal to a variable times a constant. Okay, sorry, a variable squared plus a constant is equal to a variable times a constant, right? If you rearrange this equation, if you rearrange the terms of it, And keep in mind that p here is our only unknown. We know the values of int and n. Doesn't this look very familiar? Right? You have something squared minus something plus something is equal to 0. And if you, yes, it is indeed a quadratic equation as the name implies. So if you solve this quadratic equation, you'll obtain the value of p, right? So let's just do that right now. I guess I'll just use that. Yes. Okay. So we have these. Okay, we have these values, and we have this quadratic equation down here. So I hope you guys know the quadratic formula, since most of you are secondary school students, right? Yes. So for quadratic, okay, I'll just Google it to show you guys in case you guys forgot. Wow. Yeah, so it's this, right? And if you go back to your quadratic equation, you know that A is equal to 1, 3, 3, 7, 3, 7. B is equal to minus, so C is equal to 1, 3, 3, 7 times 10. And now we want to calculate this thing, which is, okay, there's two roots, but we can just do the one with plus for now. Square root of B squared over okay, it's being angry. Okay, so now this is one root of the quadratic equation, right? So if this equation holds true, we know that one of the roots should be one of the primes p, right? And this seems like a very likely candidate. So we can test whether it's indeed a factor. Probably it is. And wow. So the remainder, the percent sign here is just taking the remainder, right? So we're taking the remainder of n when divided by this giant number, and it's 0, which means that n is divisible by this giant number. And since we know n is equal to p times q, and we have that this giant number is likely p, that means that p is equal to this, q is just equal to n divided by p. So now we have p and q, we can just do the same thing, right? We calculate pi, calculate b, which is equal to the inverse of 6 of 9, 7 minus 1, q minus 1 times q minus 1. Then we can raise our ciphertext, power of d, and then
I'm definitely watching the water. Definitely watching the water. Because I look for
wow, okay, we did it. Yay, very cool. Okay, so hopefully that was a simple enough explanation. The crux of this challenge is noticing that from this hidden value that we're given, we can construct a quadratic equation that when solved gives us one of the primes. And with one of the primes, we can find the other prime and thus fully factorize n and decrypt any ciphertext. Any questions? Okay, hopefully you guys understood that because I'm going to be moving on to another challenge now.
No, it's not.
Request.
I don't even know which what to import.
So
I use my
this challenge, right? Reduce. Okay. It's another setup similar to RSA, but you can see as Con hopefully points out, now we're only using one prime, right? So how do we solve this challenge? From the theory in the presentation in the afternoon, right? We know that if we want to kind of invert this exponentiation operation, we need to calculate the corresponding value of d. And to do that, we need to calculate phi of n. Now, what do you think phi of n is in our scenario? 0? No, it's not 0.
P minus. No, yeah, M minus 1.
N minus 1, right? Yes. Since n is one prime number, we have that phi of n is equal to n minus 1, or p minus 1, because they're the same thing, right? So if we have phi, we can just do the same thing we did earlier and decrypt the message, right? So let's try that right now. So we have phi equals to n minus 1. And we do C, D, N. Wow, okay. So this is a bit of a simpler challenge. Like, the security of RSA relies on the modulus being taught to factor, right? But if you know that the modulus is only one prime, you can just calculate phi of the modulus trivially, because it's a prime, so you know it's factorization. We still have some time to go through some challenges if you guys want.
No, reset. Just the recess. Last they like to like stuck in. Yeah, like back to what? Only time I've done that once.
I can look at it.
Alright, so we'll be writing source scripts for all the challenges. We'll be sending them in the training announcement chat later on by end of the day. So you guys don't have to worry that they go through the page.
You do try the quadratic one. I found this number for the Q, yeah, P, okay. Yeah, I found that.
But I think that like also some have problems.
So maybe
Huh?
preset lunches. Imagine not having to do it.
Oh, and it's something like
Punch you. I think I'm life be at least like cute. Starting a new thing is hard for everyone. Don't feel doubted. Who was telling me not to give up easily yesterday? I wonder who.
all you have is just something.
What?
And then they will start.
Okay, and with this, we come to the end of the critical training for today. The team is preparing a feedback form for you all to fill in. Huh? Yeah, so do complete the Google form by the end of today and show us your form to us. We appreciate your feedback, and any feedback to help us improve our workshops like this will be very beneficial for us as we plan for future things in 2026. Yeah. So do fill in the form, show us that you've done the form, and then you guys are free to leave. Yeah, and that's more or less it.
Oh, wait, hold on. You know what? We can talk outside. Let's finish this and we get out again. My brain's heard enough already.